Welcome. My name is Pat Harris. I'm the Customer Involvement Representative for Burns Harbor, and I work for the Division President, Dave Viner, and a bunch of other guys. And basically my function is to coordinate the different groups that visit our facility throughout the year, and we have over 600 of those groups visiting. Of course, the main group that visits us is our customers. We have over 250 customer visits each year, totaling about 1,700 different people. And all total, we're looking at about 7,000 people that visit our plant throughout the year for different reasons. Of course, our focus is our customers, and one of the things we do in addition to regular tours is, of course, the Steelmaking Seminar, in which you're going to have the pleasure of experiencing the next day and a half. So we're happy to have you, and as Mr. Biner said, this is an integrated steel facility, so it's a unique opportunity to have for our customers to come here and actually not just take a tour, but actually learn a little bit about the metallurgy involved in steelmaking. We're not going to make you metallurgists, but we're going to try to provide you with an understanding of the steelmaking process to the point that you can kind of have a feel for what it takes to actually make steel. So with that, I'd like to just briefly review the agenda with you so that you understand what is happening. You should have all received these either by fax or mail. But, one thing I want to just make clear, the names are bound to change. These are people that are coming out of the operations, off of their regular jobs, and sometimes things come up and they can't get away. But each one of these areas, we have 3 people that do the Steelmaking Seminar, so we have 3 people trained in each area so that if someone can't make it, someone else can fill in for them. So if we have some substitutions here, don't be surprised. We almost started out with the first substitution. Mr. Biner, he's not feeling well, and he was thinking of asking the other vice president to come down, but then I think he thought about how important this is and decided to do it anyway. Okay, if you look at the agenda, what we have is the class structured just as the steelmaking process occurs. We're going to start with the raw materials, and we're going to go right through the steelmaking process. What we'll do this morning is cover what we call the primary side of steelmaking, where we take the raw materials and we convert them in a variety of different processes into a raw steel form, which we call a slab. That you'll see this morning. We're going to have in-classroom instruction, and then you're going to go out and see those facilities. In the afternoon, you'll come back, you'll have lunch, and we'll do the same thing in the afternoon. We'll have in-classroom instruction on one of the finishing mill operations, which is the 80-inch hot strip mill. And then you'll go out and you'll see that facility. Then at the end of the day, what we do on the first day is we kind of wrap it up with some of our support groups coming in and explaining to you the importance of their role in interfacing with the operations to ensure quality and customer service to our customers. So we're going to have a little bit of that in the afternoon. Then tomorrow morning you'll do the same thing with in-classroom instruction on our cold mill complex. We have, in our cold mill complex, we have a variety of different processes there. We have, we have a 5-stand tandem mill that actually does the cold reduction. You have your pickling processes. You have continuous heat treat annealing. You have batch annealing. We have our hot dip coating line there. We have some temper pads and dual mills there. So you're going to see a variety of different operations there, and you're going to learn about all of those different processes and what they do to the steel to make the steel as our customers have ordered. So that's kind of how it's broken up, and it makes it a little bit easier for you to comprehend when you do a section or you have a lecture on a section and then you go out and see it. The most important thing I can tell you and re-emphasize what Mr. Biner said is to ask questions. Be sure you ask questions. That's going to make the class better for us and for you also. The other couple things I'd just like to mention is I'm going to give you a telephone number. If you have your coworkers or your family members that may need to get in touch with you, they can call this number and I'll get the message to you. It's area code 219-787-3651. This is a no smoking building. Right outside we do have 2 tables in our cafeteria that we do permit smoking at, and also it's going to be a pretty nice day if you want to step out the back of the building and smoke outside. There are ashtrays out there, so help yourself to that. The other thing I'd just like to cover is just a quick mention of safety. Safety is our #1 priority at Burns Harbor. Nothing, absolutely nothing comes before that. We do extend it to our visitors when we're here. We're going to have safety equipment for you. As we go out for the tours, the safety equipment will be out in the hallway area here by the stairs that we just came down. But I encourage you to make sure you wear your safety helmet and your glasses. Those are OSHA requirements. The coats, or the jackets rather, and the gloves are optional. I would recommend the jacket strongly, and also the gloves just for hanging on or holding on to the handrails. When you're out on the tours, you're going to be broken into smaller groups. People from the operations will be with you in those smaller groups to assist the tour. Be sure, if you want to see something or if you want to go off on a different path, be sure to consult with your tour leader. It's very important. We have a big facility out there, and it wouldn't take much for you to get lost and end up in a place where you really wouldn't want to be. So not to scare you, but just to make you very cautious and aware to stay together. And if you're trailing a group, don't let big gaps get between you either, because when they turn a corner, they could disappear and you could, again, not know where you are. So try to stay together in your groups and stay with your leader. And if you want to see something that's not on the regular tour path, be sure to ask your leader about seeing that particular process or operation. Okay, now that I've scared you, the next thing I want to do is just briefly go through the steelmaking process at Burns Harbor. The steelmaking process in an integrated steel mill is basically the same from one steel plant to another. You're going to have some differences in equipment, some differences in the types of products that you're going to make or produce, but basically the steelmaking process is the same. I'm going to have to shut these lights so you can see that. Thank you. As Mr. Biner said, Burns Harbor is an integrated steelmaking facility. We're going to take Mother Earth's basic 3 raw materials and convert them into a steel product that we can ship to our customer. Those raw materials include coal, limestone, and ore. At Burns Harbor, coal will be converted into coke in our coke making facility. Our coke making facility here consists of 164 coke ovens. Each one of those ovens will make about 25 tons of coke. We're going to convert coal to coke so that we can have a stronger material that's going to be used in our blast furnace operation to hold up the burden of the other 2 raw materials that have to go in there with it. And in addition, in converting coal to coke, we're getting a cleaner product that we can use in our steelmaking process. Just want to remind you that we are taking these raw materials from Mother Earth, and as Mr. Biner said, they're basically 3 different types of dirt. And then we take those dirts and we have to clean them up all through this process so that by the time we have the hot roll band or the cold roll band or cold roll sheets or coated sheets, there isn't any dirt in it at all. So all the way through the process we're doing it. The first opportunity we do that in the coke ovens is to remove some of the impurities in that coal. Limestone is going to be merged with some revert materials, and revert materials are materials such as fine, your fines off of your processes, your scale, any type of sludge material that may have an iron value in it. We recycle it. We bring it back to the sintering operation. We're going to put the limestone in there with those revert materials and also some other fine grade ores so that we can make a sinter stone. And the sinter stone will also be another material that's going to go into the blast furnace along with the coke. The limestone is a fluxing agent, a purifier. It's going to help remove, again, some of the elements that are in the raw materials when you get them from the earth. And then our other product or raw material is iron ore. That's the basic material for making steel. Our iron ore right now is mined out of Minnesota, and it comes out of the ground at about 30% iron content or Fe value. And during the pelletizing operation, we actually bring that level up to about 60%. And you're going to learn a lot more about pelletizing and limestone going into centerstone and coal going into coke in our first session this morning. The first step is in the blast furnace operation. We're going to charge in the coke, the centerstone, and the iron ore pellets. And we're going to, through this blast furnace process, injecting hot air onto the coke, we're going to generate heat and just actually melt down the centerstone and the iron ore pellets that's in there. It takes about 2 hours. We're going to produce about 600 tons of hot metal iron or liquid iron. You're going to hear those different phrases, pig iron. That's what the blast furnace does. It makes an iron product. We then put the iron into these molten submarine cars, and it's shipped over to our steelmaking operation. The steelmaking operation is going to convert that iron into steel, since we're Bethlehem Steel and not Bethlehem Iron, right? Well, we used to be Bethlehem Iron, though. And in doing that, we're going to use the basic oxygen furnace process. Basic oxygen meaning we're going to use oxygen to remove the carbon that's in the iron. There's about a 4.5% carbon level in the iron that comes out of the blast furnace. And in our steelmaking process, we're going to reduce that to about 0.03%. Carbon is one of the elements you want to have out of the metal in order to have that metal be more formable, more drawable, and so forth. So we want to remove that carbon. Basically what we do here is we charge in about 70 tons of scrap and about 250 tons of iron ore into this furnace, and then we inject oxygen at supersonic speeds, and what happens is there's an exothermic reaction to that oxygen when it gets in with the carbon, manganese, silicon, and so forth, and your heat generates and you're actually burning off the carbon. That's actually what that process entails. It takes about 20 minutes, and at the end of that time we will have about 305 tons of liquid steel. We'll put it into a ladle. That ladle will then have the steel refined. We can argon stir that steel in the ladle. We can vacuum degas that steel. We can desulfurize, take some of the sulfur level out of that steel in the ladle, and so forth. But once we have refined the steel in the ladle, it goes to either our continuous casting process or into our teaming aisles, where we're going to make a slab. The entire top half of this chart is our primary side of steelmaking. This is what we're going to cover this morning. You're going to talk about this in this classroom, and then you're going to go out and you're going to see all these different operations. And continuous casting takes about a half an hour to convert our liquid steel from the ladle into a slab form. And the ingot teaming method, we're pouring steel into individual molds, allowing that steel to solidify, which can take up to 24 hours and so forth. And then we're stripping that mold away from that steel. You have what's called an ingot. That ingot is then reheated and then rolled into a slab. So there's a vast difference in time of the two processes and yield. But the thing we have here is the ability to make very heavy gauge plates, which we have a market for at Bethlehem Steel. So we are using this method about 15 to 20% of the time for those specific applications that we cannot use the continuous casting method for. But once we have a slab by either method, it will go into our finishing mill operations, either the 160-inch or 110-inch plate mill, be rolled into a plate and shipped to our customer, or we'll go over to our 80-inch hot strip mill, where we will make a hot band. That hot band can ship to our customer, but over 50% of what we make in the hot mill will continue on in the steelmaking process into our cold mill complex, where we start out pickling that coil, cleaning it up, taking some of the scale off. It goes into our 5-stand tandem mill for coal reduction, going to reduce the steel even further. And then after doing that, we need to anneal it, so it will go into either continuous heat treat annealing or into batch annealing. And from there, it can go into a variety of different operations. Also from the coal or the 5-stand tandem mill, that coil can go into our hot dip coating line, which has its own in-line annealing furnaces, where it will receive the annealing at that point and be made into a hot dip coated product. We're no longer doing electrogalvanizing at Burns Harbor. That's being done out of our Walbridge, Ohio facility. But that's a basic overview of the steelmaking process at the Burns Harbor plant. How did that all happen? I'll take just a couple minutes and run you through the history of the building of Burns Harbor. The announcement was made in 1962 to construct a plant here at Burns Harbor, Indiana. And that was after many studies were performed to evaluate the market conditions. And at that time, the Midwest area was growing by leaps and bounds in the consumption of steel. So Bethlehem Steel had its facilities mainly on the East Coast and West Coast. And in looking at the Midwest consumption, it was decided that we better get ourselves located out here to actually service our customers better. So a site was located, and in 1962, the announcement was made that we were going to start construction. A couple years later, we actually started up our first facility, which is the 160-inch plate mill. During that time, the plate market was very, very strong, the strongest of the other products, in that there was a lot of building and construction going on at that time, which requires a plate product. The theory here was to build a plant backwards. We would bring in slabs from our sister plants at Sparrows Point in Baltimore and Lackawanna facility in Buffalo, New York. We'd ship the slabs in here, roll them into plates, and we would send those out to our customers. In building the plant backwards, what you do is avoid things like building a BOF shop or a blast furnace. The blast furnace, you're making 600 tons a batch of iron, and you don't have your BOF built, so where does it go? So the theory was to build backwards and have a place for the steel to go when it completes. 1 year later, the cold roll, sheet, and tin mill facility started up, and again we had to ship in now hot bands for this facility in order to roll those hot bands into a cold roll product and then ship it to our customers. By 1966, we had completed our finishing mill facilities. We had our 80-inch hot strip mill in place that could now roll the hot bands for our cold mill complex, and also our 160-inch plate mill was making plates for our customers. Again, though, the hot mill had to have the slabs brought in to service it from our sister plants back east. In 1969, we became a fully integrated steelmaking facility, which allowed us now to make our own raw steel product of a slab that we could now feed into our finishing mills. We started up one coke battery with 82 ovens, one blast furnace to convert the iron ore pellets into a liquid iron or a hot metal product. That blast furnace's rated capacity at the time was about 3,500 tons of hot metal per day. Our steelmaking shop had 2 BOF vessels in them. BOF again refers to basic oxygen furnace. We did not have continuous casting technology at that time, so we built all of these support facilities to actually make our slabs by the ingot teaming method. In 72, expansion of our primary side included our second coke battery and a second blast furnace. Further expansion in 1975 actually brought in our sintering operation that allowed us now to recycle and recover as much iron value as we could in the products that came, or the byproducts that come off of each operation. And also we had our first continuous caster installed at our steelmaking division. That caster was making about 35% of the slabs coming out of our steelmaking division. In 78, we had the startup of our second plate mill facility The two plate mills give the Burns Harbor division the largest shear plate capacity in the United States. And we also added our third vessel to our BOF shop. In the early 80s, Bethlehem Steel and the steel industry as a whole went through some very difficult times, and we had to go through a restructuring process to actually become more efficient. We were being threatened by substitute materials in aluminum and plastics, and we also were threatened by imports. So we had to really look at how we were doing business, and one of the theories was, instead of having all of our plants trying to make all of the products for all the customers, we'd have those plants focus on industries that they could service best. Burns Harbor became a light, flat roll, and plate producer. We actually closed down our Lackawanna facility back in Buffalo, New York, that at that time employed over 22,000 people. The galvanizing line at that facility was fairly new, and rather than shutting it down, it administratively became part of the Burns Harbor division. So the superintendent of that line, 500 miles away, reports to our division president at Burns Harbor. One other thing we did was, at that time up to that time, we had been making tin plate out of Burns Harbor and tin plate out of Sparrows Point. Well, in relooking it, it was decided that all of our customers could be serviced out of Sparrows Point that bought tin plate products. So that tinning line was shut down, and all those customers would now order their tin plate from Sparrows Point. But in closing down that line, 1 year later, we converted that line into an electric galvanizing line. Corrosion-resistant materials were becoming a must-have situation for the automotive industry, and if we were going to keep automotive customers as one of our basic industries here, then we would have to have those types of facilities. So we did convert that line into an EGL facility. In 1986, and in keeping in line with our strategy for the industries that we wanted to service, we actually started up a second caster in our steelmaking shop. The two casters together now, as I said, convert about 80 to 85% of the steel, of the liquid steel coming out of the steelmaking shop, into slab form. Actually, in 1989, we started up a vacuum degasser in our steelmaking division, which, again, in line with our new strategy, if you're going to make interstitial-free, ultra-low carbon steels, you have to have a vacuum degasser to do that. And even though it looks like a very small piece of that entire puzzle, it was very key to our overall market strategy. Actually, in December of 1992, we started up the hot dip coating facility at the Burns Harbor division. And again, this is in keeping with our new strategy and the types of industries and markets that we wanted to serve. This is Burns Harbor today. This is the most efficient plant layout for a steelmaking facility in the world. You're looking at north and south about 1.5 miles, west to east, it's about 3.5 miles. It's very compact for a steel company that can ship over 5 million tons of steel per year. The other thing about this layout is that we receive all of the raw materials on the west side of the steelmaking facility. Once it's into this plant and into the process, those materials flow one direction. There's no backtracking of that material, west to east. The other key about the layout and being very compact, you're moving very, very large volumes of material very short distances, not 5 miles down the road. If you've been in other steelmaking companies or their plants, you may have witnessed materials having to backtrack and go long distances between one operation to the next. And basically, that's because when they were built for the technology that was available at the time, and so the land that was purchased was more than likely only purchased for that technology. When Burns Harbor was built, we looked out 75 to 100 years into the future at any possible technology that may come on, And as the plant was being laid out, there was a place for everything that could come on or be included in this facility. As we were building this plant, for instance, the hot dip coating line went in right where it's supposed to be. The 5-stand tandem mill is right here. It receives product off the tandem mill off onto that line. So everything goes in right where it's supposed to be in the steelmaking process at Burns Harbor. Some basic stats about Burns Harbor. Our liquid steel capability is actually up towards 6 million tons per year. We're going to continuous cast 80 to 85% of that liquid steel into slab form by both casters. And in 1994, we actually shipped over 5 million tons of steel out of Burns Harbor. The employee breakdown is as you see there. The one comment I will make is the average age is fairly young for a steel company. The products and markets that we serve are, as you see, we have basically 4 products coming out of Burns Harbor. We have plates, we have hot roll bands and sheets, we have cold roll sheets, and we have a coated product. The coated product will be either electrogalvanized or hot dip galvanized. And this is a nice aerial view of Burns Harbor just to kind of show you we're surrounded on 3 sides by a national park. And actually we were here first, just so that you know that. The park came later. And the park actually came as a result of not wanting the residents in the area not wanting any further industry to build along the lake shore. So it was sort of established after we were here. But in any case, we do sit right in the middle of a national park, which makes our citizenship to this community very important, and our performance as far as environmental very, very important. Are there any questions? Okay, we're going to take a 15-minute break, allow our next presenter to come in and get set for you for the next section. The next section will be on raw materials. He's going to explain to you in more detail about those 3 raw materials and actually the preparation of those raw materials for the steelmaking process. Then he's going to go into the iron making side of it, actually taking those raw materials, putting them into the blast furnace and making an iron product. So,
good morning.
Good morning.
I was going to say let's have fun this morning. And if you have any good questions, we'll find the answer if I can't answer them. I've been with Bethlehem Steel for 25 years, so all of it's been in the primary end. And we have a very good speaker that talks about steelmaking this morning along with me, so it should be interesting. Like Pat said, I'm going to talk about the primary end, and that's broke down into different areas. We have the material handling section, and we see a lot of materials coming in. We're an integrated steel mill. We take everything out of the ground and make a product. And we have 2 methods of bringing our materials in. We have the lake with boats and barges, which is our iron ore, our calcite, our dolomite, and then we have a railroad system that brings in all our coals, and we do by coke. That material, well, I'll break it down. We'll go into the coke ovens first, where we take the coal and we make coke. Coke is a very vital function in the operation of the blast furnace, and that's our goal. We're going to finish up making liquid iron. We have a center plant at Burns Harbor. The center plant's like a garbage can. We take all the recycled materials that we use and we use them back in the process because it all has iron-bearing material in it, and we want to make iron with our material. And then everything eventually ends up at the blast furnace. If you have any questions, don't hesitate. Just raise your hand. Can everybody hear me? Okay. Yes, sir.
You said you buy coke.
Yes.
You also make coke.
Yes.
That means you can't produce enough coke.
Correct. And we'll get into that a little bit more. We added coal injection to our blast furnace, and that supplemented our coke shortage. but we still do not make enough coke for the blast furnaces we have in operation at Burns Harbor. We do buy coke from our sister plant at Lackawanna, though. Oh, look at the button here. I'm doing it wrong. Give you an example of where all the materials come from. We're right here. We get all our iron ore pellets from Hibbing Mine. Now we have to process that because iron ore, usually you want iron with at least 50% or higher iron in the product. So they process and make pellets out of it, and it's about 65% iron in the pellets. Okay? And we get our calcite and our dolomite from Michigan. They are the fluxes we use in the blast furnace. They're the chemical cleaners. They remove all the phosphorus, the silica, some of the sulfur out of the iron to make elemental iron. Now we're into the coal region where we get most of our coals. We just went through a coal blend change, and we used to get coal from Canada. We don't get coal from Canada anymore. We get it mostly all from the United States right now. And I'll go into that in a little more detail. But this gives you an idea of how the coal and all the materials, the coal comes in by rail, the pellets and the limestone comes in by boat. It's a nice little system. Now, what's it take to make a ton of iron? Am I walking too far away or? Okay. We use a ton of pellets, about 65% iron. We use sinter. Now, sinter is that product where we take all the waste and the reverts. We also mix in some iron ore fines, and we make a product called sinter, which is about 65% iron. That's where we add the fluxes, the dolomite and the calcite, into the mix. Then we use coke. Coke is a viable product in the blast furnace, and because it serves two purposes. It holds the burden, and we'll get into that, because everything's coming down the blast furnace from the top to the bottom, and that's holding that burden in the furnace. And the other thing about coke is it's probably 92% carbon. And carbon is what reduces the iron oxide into iron. Okay? Coal. We inject coal now into the furnace. Coal replaces coke. As you can see, the reason why I have this written like this, we have two blast furnaces at Burns Harbor. One uses more coal than the other one. And we'll get into that in a little more detail because it has some structurally different characteristics of it, the way it was built, that it can add more coal to that furnace. And that replaces coke. Used to be, we used about 900 pounds of coke to make a ton of iron. We use air, the hot blast. That's the blast that comes in and reduces the iron. And then we supplement with oxygen. Okay? Now, I apologize for the picture, but here's the blast furnace. Here's where we're making iron. We make the pellets, we make the sinter, and we'll talk about these individual things. We're going to go into the coke oven, where we take the coal, put it in the ovens, and make coke. This is, can everybody see that? We're kind of blessed at Burns Harbor because we have a very good system as far as the coke making operation. We receive all our coal by rail, and it's loaded, and then you'll see it. We have big fields we call a big coal field where we store our coal in the ground. We handle every coal individually, and we process every coal individually. And then when I say process, we have two operations. We have what we call a Bradford breaker, which is a big rotating drum with holes in it. And it takes the coal from about a 2-inch size, bigger than 2-inch, down to 2-inch, because the holes in there are 2-inch. So as that coal's banging around in there, the 2-inch coal falls through. Then we have 3 compactors. Now, the 3 compactors are actually hammer mills, rotating on a wheel with hammers on them. The coal comes in and we crush it. We like to crush the coal to about 83% through 1/8 of an inch. That gives us the right pulverization so we can control the blend and we can control the bulk density and a lot of other variables that make good coke. And then all that process, we store our coal in silos. And then from there, we have weigh feeders that individually control each silo that allow the coal to be proportioned. We don't go in, it's like making a cake, only we have a couple more mixes than a cake mix would. Okay. Then we store our coal in the individual bins. One sad thing about, wow, the tourist guys, I can't take you on the coke oven, I can't take you in the center plant, and I don't take you into the blast furnace. But we get a flavor for it. You'll see the coke batteries. We'll drive past the center plant, and then we go to a place called J5, which gives you a panoramic view of the primary operation. Now, if you could have seen this slide, this is our coal field. It's very huge. And back over here is the lake, and then here's an unloader for the barges and the ships that come in. And back in here is our car dumper. It's a rotary dumper. It just takes the whole railroad car and turns it over and dumps it. Okay? And this is one of the devices we use to stack our coals and reclaim our coals. It's got a conveyor belt that when the coal comes in, it feeds and dumps onto the pile. Then it has a paddle wheel that turns and reclaims the coal. Like I say, every coal is individually treated till we blend it. And here are the silos. These are concrete silos. They hold about 15 tons of coal each. So it's kind of a 24-hour operation. And then this conveyor belt feeds from the coal handling over to the battery. This is a 2,000-ton hopper or silo or whatever you want to call it that holds the coal we put into the battery. Okay. Now we're going to talk about a coke battery. We have 2 coke batteries at Burns Harbor. Anybody ever worked in a steel mill? Oh, that's sad. It's a neat experience. This is a battery. And basically a battery is, if you think, give you an example. You ever see wooden matchboxes? If you take a wooden matchbox and you take 82 of them and you line them up, that would represent a battery. And when you push it open, that would be the oven where we put the coal in. Okay? And in between those boxes is the heating system where we heat the coal. But this is the pusher side of the battery. This big monster here, which is about 3 stories high. I came from a little plant where we had little batteries, 4-meter batteries, and there wasn't many steps. Now, when I came to Burns Harbor, we had 6-meter batteries. I thought, my God, they had an extra flight of stairs. So it was different. But this machine is used to push the coke out after it's made. Okay? Another thing about, and I'll brag about Burns Harbor, before '93, you wouldn't have seen a picture like that. Because you'd see brown stuff coming out of these doors. We've done a lot of good work as far as environmental control at Burns Harbor. And it's been positive. It's been a very good experience. Okay, this gives you kind of a cross-section. That picture we looked at was the front right here. This is that big pusher machine. Okay, this is the oven chamber. The oven chamber is 20 feet high, it's 50 feet long, and it's 18 inches wide on the average. Okay, and underneath it is our regenerator section, and beside it, or adjacent to it, is our heating system. Okay, and on the top is what we call a Larry car, or coal charging car. This contains the coal we're going to put in the oven, and we do it through these little holes. Well, actually, they're 18 inches in diameter, so they're not really little. And we generate gas. In the coal, we have volatile matter. And volatile matter is, when the coal's heated, it gives off the gases. And that contains the tars, the nitrogens, the hydrogens, the hydrocarbons that we use and we process to make other things. And we'll get into that too. But what I wanted to show you is those gases come off through this piping system, and we collect those gases. Okay? This is an example, and I hope you can see it. This was that Larry car. Here's the coal bin, and here's the man. So you can see how big. It's over 400,000 tons. It's a huge device. Yes, sir.
Lights a little bit better. We turn the lights down.
Try it. Yeah, like that. Will that hurt you guys back there? Okay. Yeah, that's better. Thank you very much. So this is a Larry, and it has 4 hoppers. And as you can see, we have 4 openings in the oven tops. And that's how we fill the car up. The reason why I show you this slide is, see the yellow clothes and the face shield and the respirator? It's all required equipment for the coke oven. Now we get into the meat of coke oven. This chamber right here is where the coke goes. In between is where we heat the coke. There's flues. We have 32 flues in the one battery, and we have 30 flues in the other battery. The gas comes from a pipe underneath. This is called an underjet battery. You see, sometimes you'll see the gas come in from the bottom here. But this is an underjet battery, so the gas is fed up. We have what we call regenerators underneath the heating system. That's where the air comes, because you need gas and air and heat for combustion. But we use the heat from the waste gas to heat the incoming air so we get better combustion. That's kind of a hairy subject, and if you don't understand it, we can talk about it later, but it's interesting, but it's not needed for this class. But we mix, as you can see, these air ports, and this is not a very good drawing, but the gases come in, mix with the air in one flue, then the waste gas, the product of combustion, goes down through the other flue and comes out the adjacent regenerator, okay, and out the stack. Then that regenerator heats up, and we reverse every 20 minutes, and we use the other regenerator to heat the air. So every other flue is burning, and then on the off side, every odd flue is burning. And that heats the coke from the wall, both walls, in. Okay, now this is the coking process. We have the Larry car, and we have an empty oven. Volume about 1,390 cubic feet. We'll take 34 tons of coal, and we put it into the oven. Now we put it in a certain way to basically for pollution control. We stage charge it. We don't put all the coal in at once. We put the 2 outside hoppers in, and then we put the lids back on, then we put the second hopper in, put the lid on, then we put the third hopper in. That way we can control the emissions. Then on this pusher machine, there's a bar, and that bar just goes right across and levels the top of the peaks. Okay, we call it leveling. So, as you can see what it does, though, it gives us a nice little opening for those volatile gases that are coming off during the coking cycle. We can collect them. If we don't, it causes pressure in the oven, and then we can have more emissions. So we do that. Then the coal sits in there for 18 hours. Our coking rate is 18 hours, inch an hour coke. And the coal goes through that transformation where it becomes coal. It almost becomes liquid at the temperatures we coke it out at. Then it becomes solid again, which we call coke. But when the process, all the volatile matter and the moisture is drawn out of the coal. So it's probably, like I say, almost 90-some% pure carbon. And the rest is ash and a little bit of sulfur. Okay? The coke itself will come out about 2,000 degrees Fahrenheit. Then after it sits in there, we have devices on the pusher machine to remove the oven door on both sides. And then we have a guide, we call a coke guide. And all it is 2 slats, walls, that act as an extension of the oven. The coke is pushed by this ram on this pusher, as you can see, through the oven, and it stays as a mass. And it's collected into what we call a one-spot quench car. And it's like I said, it comes out about 2,000 degrees Fahrenheit. So we have to cool that so we can convey it to the blast furnace. So we take it down to what we call a quench station, and we quench it with coke. Anywhere from 8,000 to 10,000 gallons of water. Okay. Now, this is an oven with the door off. So this is the coke inside the oven. Now, if you were standing as close as I am to this oven, you'd be having a little sweat on here. It'd be a little warm. But as you can see the vertical split in the middle? That's because the coal is being coked from the outside walls in. And in your book, we talk about volatile matter. We use different types of volatile matter because they have different characteristics. Well, you don't have to look through it now. You can read that tonight. You don't have anything to do. We have what we call a low vol coal. And that's where the volatile matter is about 21% of the coal blend, or the coal itself. Then we have what we call a medium vol, which is between 21, 22 to about 28%. Then we have a high vol coal, which is about 28 to 32% volatile matter. Now these coals have different characteristics, and that's why we use them. The low vol coal is a very good coal because it makes a very strong coke. Now remember, we're using the coke to hold the burden up, so we want something strong so it doesn't, disintegrate on the way down the blast furnace in the furnace. But the thing about low vol coal is it expands when you heat it. So if you've got an 18-inch oven and you don't have any room for expansion, that can cause damage to your oven wall. Because all that's inside a coke oven is brick. There's about 3 million bricks making up a coke battery. Now high vol has a little different characteristics. It doesn't make a strong coke, but it has a binding ability. When it goes through that phase where it's becoming liquid, it binds with the low vol coals, and together it makes a nice strong coke. If you were to take high vol and just put it in an oven, it would work because it actually shrinks when you heat it, but it makes a weak coke. We need to add the low vol and the high vol. Now you see, I didn't mention medium vol, and we do discuss it in the book. With our new coal blend, we've gotten away from using medium vol coals. We're back to using high vols and low vol coals, and which it's just a management decision. Okay. Now after the coke is caught in the pan, we take it down to this tower, and we'll get to see this today. This is where the coke is sprayed with water. And actually, believe it or not, there's a science in that, because we want to control the moisture of the coke for two reasons. We want to control it from a fuel standpoint, because we don't want to be giving the blast furnace high moistures, and then they have to use their fuel to get rid of the water. And secondly, we want to control the moisture so we eliminate all variabilities in the coke. One of the key things to making coke is no variabilities, no changes. You want everything to be consistent, from coal handling to coke making to the final product. That way the blast furnace doesn't have to react to any changes. If the coke oven does a change, the blast furnace finds out right away, because it happens right there in the furnace. Okay. Now after the coke is quenched, we have a wharf, which is an incline. It's on an incline, and the coke lays in there, and we have a plow that we use to remove the coke from the wharf. Okay, the second part of our coke making, and I'm sorry guys, I failed to, is this going to hurt you walking over here? I brought some samples along. This is the coal, and this is what we put in the oven. This is actually the crushed coal, so if you want to pass that around, you can look at it, and here is some coke. Now you notice the size of the coke. It takes that form where it finishes heating and goes. That's what coke would look like. And that's the kind we want to use in the blast furnace. We want to use the bigger pieces instead of the little pieces because we're blowing air up into the furnace, and we need what we call permeability. We need the ability for that air to get up through the furnace. Okay? Now we'll get into the coal chemical section. We're generating all this gas, and we make about 90 million cubic feet of gas a day. It's called coke oven gas. And it comes off the batteries, and we process it. First of all, we cool the gas down. When we cool the gas down, we get a lot of tar out of the gas. And tar is what it is. They use it to make electric binders, electrodes in electric furnaces, and they use it on the roads. It's just tar. Be very careful with that, folks. That'll stain your clothes. And in this process, we have what we call exhausters. They're just turbo compressors. They suck the gas off through the exhausters, and then they push the gas through the rest of the system. Okay? Now we have 4 tar precipitators, and they're electric. They have these bars, and there's about 109 in each one of the tar precipitators. And as the gas is coming through, these are electrified. And the tar gets electric charge, and they collect on these rods. So we can remove probably 99.99% of the tar in the gas, because we don't want any tar in the gas. Okay, so we got rid of all the tar. Now we come over to these 2 yellow things, which are ammonium absorbers. There's a lot of nitrogen in coal. And nitrogen is a product that we use, or we make a byproduct from, and we call it ammonium sulfate. Okay? And being the fact that it's got a lot of nitrogen in it, we sell it to fertilizer farmers, and they use it. Couple little anecdotes. I took some of that home, and you don't, it's very high in nitrogen. It's not the 10, 20, 10, it's probably 40 nitrogen. And you just take a light amount and put it on your grass, and you either have 2 results. Either it turns brown, or you're mowing it every day. So I got away from doing that. The other thing is I put it on a tomato plant. And man, I had this tree growing. I mean, it was huge. It was way above my head. I think it got about 8 feet tall. There was not one tomato on that tree. I was just, you know, I see this thing growing, I think, God, these tomatoes are going to be huge. Not one tomato. Okay. And then lastly, when we add the sulfuric acid, we heat the gas up. So we process it with waste ammonia. We use a debenzylized material to remove the naphthalenes and some of the higher carbons, and also to cool the gas. Because when we clean or finish cleaning the gas, 30% of the gas we make at the coke oven goes back to underfiring the coke oven. And then we send the rest to the mills, using reheat furnaces all over the mills. So it is a viable product. And I think if they were to ever shut down the coke ovens, besides losing coke, they would lose that gas ability. Okay. Are there any questions about the coke oven? Yes, sir.
I saw your materials and your utility bill. It seems very low, $300,000 a year. That because you usually allow the products to fire. Very much so.
About 80% of everything used in the mill comes from the coke ovens, either in the form of coke for fuel in the furnace or the gases we use or make in the coke battery, yes. And the thing about the coke oven gas, it has a BTU value of about 540. Natural gas has a BTU value of about 1,000. So, you know, it's not a bad gas. Okay, here's some of the parameters we look at in the coke. The volatile matter, we don't want any volatile matter in the coke. We want to coke all that out. We want to get rid of all that. The ash, now this is controlled by the coal. The sulfur is controlled by the coal. We use low sulfur coals, and we use low sulfur or low ash coals. We pay a little more premium for it, but it gives us what we want. size is very important because we're looking at a certain size going into the blast furnace. Moisture, we talked about that earlier. We don't want the blast furnace to be using their fuel to get rid of our moisture. And then stability is that strength number. And they actually measure that. They do a lab test, and that's an interesting thing because the blast furnace looks at stability and they say, you're not giving us high enough stability. And the coke oven says, we're doing the best we can. So it gets a little interesting, but now we're going from, we'll go to the center plant. The center plant's a little unique place, kind of there. But what they do is they take all the reverts. And guys, we make a lot of reverts. Okay, here's some mill scale. When the thing goes through the mill, we get the scale off of it. It's got iron in it. So we ship that to the center plant. Now we have this. Well, we supplement the center plant with iron ore fines. Because what we do, and I'll get into it, is we can take the fines and we make a product from it. Okay? Here's some BOF slag. There's iron in that, believe it or not, and we use that in the process. It also has some fluxes in it that we can use in the furnaces. Okay? And then here's limestone. Basically, right now we're using dolomite and calcite, and I think this is just calcite, calcium carbonate. Okay? Now, the way they do it is they take all these materials and they size them, and they make what they call a bedded POW. This device will make a POW. See how we have little triangles here? Each one of those are a different material. Some might be iron ore fines, some might be BOF slag, mill scale. We use the filter cake, the dust from the blast furnace when we clean the gas, and all that goes into making a POW. Now this POW, when they're done making it, is about 50,000 tons of material. So they make 2 POWs. Well, actually they have 2 POWs. One they're making and one they're reclaiming from. They have this device that has little arms or fingers, and it vibrates along, and as it does, it knocks the material down, and this bucket wheel picks it up and stores it into what we call our bins for making sinter. Now here's a picture. Here's a picture of us making a POW, and here's a picture of us reclaiming a POW. See how this was a little bit lighter than this? So that might be like a breeze or some kind of material. Okay. Now the center plant is kind of a neat operation. They take all the storage material from the POWs, the raw materials, and we have some other things. We have iron ore fines that we use for trim. We have coke breeze we use for trim, and coke breeze is a byproduct of the coke oven. They take this material and they put it through a micropalletizer, which is a nice fancy name, but all it does is it takes the powder material and makes it into little tiny balls, so that when we put it on the center machine, which is a long steel conveyor belt, it has voids, and we need the voids or the for permeability, because what happens, the material feeds on this side. We have an ignition furnace. We actually light the material. And this conveyor belt's moving, it varies. Probably about 300, no, I don't want to say that. What do I want to say? Maybe about 200 feet an hour. Okay? Moving this way. And it has a bed of about 12 to 16 inches of this material, the center material. Okay? And we've ignited it. Now underneath here is a set of wind boxes connected to a fan. And it's sucking air down through that center strand. And as it sucks the air, it's drawing the combustion down through the POW. So by the time it starts here till it gets to the end of the strand, all that center has been heated and cooked. Okay? Then it comes off the strand and we screen it. We screen it to about 3 plus 3/16. And then what is greater than plus 3/16, we put on a big rotating cooler. We have to cool this material because it comes off the center strand, about 2,700 degrees Fahrenheit. It's pretty hot. And then when we cool it, we screen it again for, we screen it for plus 1/4 inch, then we screen it for plus 3/16 to feed to the furnace. So I got my numbers a little bit messed up. But we screen it again, and then that's another part of the blast furnace burden. This is what center looks like. Okay? And that has probably about 60 to 65% carbon in it. And it also has the fluxes that we need to remove the impurities out of the iron oxide to make iron. Now we got a couple pictures. I hope you can see them, guys. This is that conveyor belt. It's made out of metal, steel, or cast. And this is the bed. And we have this ignition furnace. So this material is ignited, and it draws along. And as it's drawing on, the air sucking it through, causing the material to cook. Okay? And that's why we need it in little balls, so the air will suck through and draw the flame down, or the heat down. And here's what it looks like when it comes off. Now they got a little door up there, and you open the little door and it blasts you, because it's warm. I mean, this is not a nasty, this is kind of a nasty place to be. That's what center looks like coming off the strand. They screen it, and then they cool it. And they cool it on this big, rotating conveyor. You see we add some water to cool it, speed up the cooling, and that's how center's made. So it gives us the ability to use a lot of materials. We have some quality variables in center. The stone equivalent, that has to do with the fluxes and how we want to control the chemistry in the furnace. Silica is important, and I don't want to beat you to death with that because my friend from steelmaking just spends all day on that. So you'll get a lot about silicon. And strength. About 33% of the burden in the blast furnace is center. So you want it to have some strength too. Okay? And that's what they look for, is strength. Now I guess we're getting to the big guy, the blast furnace, where everything happens, where we make iron. This is a structural view of the blast furnace. Now, blast furnace is just a vessel, big, tall vessel, 125 feet tall. Okay? Down in here, this is the hearth area. This is where all the liquids, the iron and the slag form, and we'll talk about that in some detail. This is all brick lined, and it's also water cooled. If we didn't cool it with water, she'd melt, because we're getting some pretty warm temperatures in here. And we also have what we call cooling plates. They help cool the furnace to control the temperature of the walls. Now, remember when I showed you that first slide and I said we use a little more coal in the one furnace versus the other furnace? Well, when we relined the furnace that uses more coal, we put a little more sophisticated cooling plate in there. It absorbs more heat. So we can throw more coal in there, because coal will generate a higher temperature in the blast furnace. We're talking in the range of 3,800 degrees Fahrenheit. Very warm. Okay? Now at the top, and you can't see it in this drawing, but we'll get into it, we have a double bell system. The material all comes in the top, and the iron comes out the bottom with slag. And I'll show you another drawing of this material, this double bell system, in a minute. But the other thing is, too, we generate gas. We make what we call blast furnace gas. Now, blast furnace gas has a BTU value of about 85. It's not a big, you know, it's not going to heat your house unless you have a real big line to feed your furnace, but we make a lot of it. We make about 250,000 cubic feet an hour. And we do use blast furnace gas. We use blast furnace gas in the blast furnaces, and we also ship some down to the coke batteries, because we mix it with the coke oven gas to lower the BTU value, because we want a longer flame. And we get that with blast furnace gas. If you remember, the coke battery wall is 20 feet high, and we want the oven wall from floor to ceiling to be almost identical, same temperature. We want very little differential. So we use that blast furnace gas, and it gives us a long, lazier flame, so we can heat the wall more uniformly. And it's worked well for us. Okay. This is an outer view of the blast furnace. As you can see, it shows the shell. This pipe going around here is a bustle pipe. That's where all the air is injected into the blast furnace. And inside the blast furnace, we have these pipes, and they call them tweers. I don't know where that name came from, but that's what they call them. And this is where the blast, which is a hot blast, or the term blast furnace, comes from. So you have material coming through, constantly being fed, the hot air going up through, and it's a constant reactor. It just keeps going and going and going. Now this drawing gives you a little better idea, and it didn't get the effect I wanted. But we have what we call a double bell system. We have a large bell, which you can see, and we have a small bell. So we'll take material, put it on the small bell, and with the large bell closed, we'll open up the small bell and allow that material to fall onto the large bell. Then the small bell closes, and the large bell opens, and the material goes into the furnace. That way we keep all gases inside the furnace. Okay. Now, why does this look the way it does? Actually, each one of these phases or colors represent a different material. This one could be iron ore, this one could be coke, and this one could be sinter. And they have a prescribed way of filling the furnace. Okay? Now, when the material gets up into here, it's about 300 degrees Fahrenheit. It's just starting to get hot. And now the material's falling down. Now, basically the only thing that's left at the bottom, besides the liquid iron, is coke. This furnace is full of coke. Okay? And as this material comes down, it gets into this cohesive zone, or this active zone, where the temperatures are in the 2,000 degrees, 2,500, 3,000 degrees. The iron ore is starting to melt, or smelt. It's mixing with the fluxes, and we're making a liquid product. Okay, now where's the coke come in? For all you chemists, the coke adds with the air to make carbon monoxide. The carbon monoxide reacts with the iron oxide to make elemental iron and carbon dioxide. So we keep adding more air, that keeps adding with the carbon, makes more carbon monoxide, and it keeps processing. Now where's the calcite and the dolomite come in? They're the fluxes that are removing the undesirable products, the manganese, the phosphorus, and all that stuff. The silicas, we're taking that out. Now what happens is we'll get two products at the bottom of the furnace. We get liquid iron, and we get what's called slag. Slag has all the reverts, all the nasties we don't want in the iron. Okay? And the nice thing about it is the slag floats on top of the iron. Okay? But you can see, now here's the tweers, and each furnace has 28 tweers. And we're putting in about 180,000 cubic feet of air a minute. So we got a pretty good blast going in there. The coke and all the materials falling down, and that's what's happening. You guys with me on that? Is that? Okay, good. Sometimes I have difficulty explaining that, but okay. The other thing about coal is injected at the tweers. And what is coal? Coal's carbon with volatile matters in it. But we use a low vol coal in our injection, so we only have about 21% volatile matter. And when you're talking the temperatures we're talking here, you're going to volatile, you're going to burn off all that material, that volatile matter in there. So, and it replaces coke about pound for pound. You inject a pound of coal, that's less than a pound of coke you need to add to the furnace. But now think about it. If we were to add a whole bunch of coal and had a real weak coke, we couldn't do that because the coke would not hold the burden. So you have to have the best of both worlds. You have to have a better coke to add more coal. And then the other thing is we still have some limitation on the structure of our furnaces to be able to handle the extra heat in the blast furnace. The iron comes out about 3,000 degrees, Mr. Keith? 2,500? 25, well, that's because it's in the ladle car and it moves over. It's about 2,900 degrees, 3,000 degrees. And I apologize for this one. We have a unique system. The old blast furnaces used to use those buckets. They call them skip cars, where they fill up material and run them up. We actually have a conveyor belt that feeds to the top of the furnace. Okay, and if you could see this is the furnace. Same thing I showed you. Material coming in, the iron going into the subcars to be shipped to the BOF, the slag going into a pit where we quench it with water. We have a contractor that comes in, crushes it, and you might have it on your roads because that's what they use it for, road slag, most of it. The other thing about it is the gases coming off are treated. We remove the moisture and we remove all the dust particles. So we reuse the gas. Now some of the gas we use in the stoves. You'll see 4 stoves for each furnace. And inside these stoves, they're just big domes. And they're full of bricks. And we use the blast furnace gas to heat the bricks up. And we'll be heating 2 stoves up and using 2 stoves for the hot blast. We heat the bricks up so that the air coming out of the stoves is about 2,000 degrees Fahrenheit. So when we blast the air into the furnace, we're using a hot blast. So everything in there is hot. Okay? And that's where we use a lot of the blast furnace gas besides coke oven. And they have the ability to use blast furnace gas through the plant. I apologize for that. Now here's a nice picture. This is a picture of them tapping a blast furnace. So you can see having all you guys standing there and all of a sudden they go tap a blast furnace and I see 10 of you running because it can get a little exciting. You know, but they actually drill a hole. This device here takes it and drills a hole into the hearth where the iron is, and it'll actually spark like that, and then it comes down this path or trough, and the iron and slag are separated. The iron going into the subcars to be shipped to the BOF, and the slag going into the slag pit. And here's another picture when it usually just happens when you first tap. After it's calmed down, it continually runs iron and slag. Now on our furnaces, we have 2 tap holes, one on opposite sides of each other. And they try and tap probably 80% of the time. We want to make iron. So we are constantly filling it up and emptying it out. Okay, coal injection. This is probably the only slide that come out nice. This is a complicated type gizmo, but basically what we do is we take coal, we put it through a mill, we crush it. We have the ability to use either pulverized coal or granular coal. And I think if you look in your books, it differentiates between the two. We like to use granular. It's a little bigger product. We take it and we crush it in the mill and we add a heating gas to it. So we want to dry the moisture off. We want to have a very low moisture in the coal, about 1 to 3% moisture. We put it through a cyclone to separate the gases. We're using the heat to dry the coal. and also through a bag house. So we separate the coals from the hot gases. We go through and we screen it. We want to size the coal because we're going through a set system. Then they, in turn, go into 4 silos, 2 feeding our one furnace, the other 2 feeding our second furnace. And then at the bottom we have 28 little screw feeders that proportion the amount of coal we want to go into that tuer, and we blow it through with air. Hopefully you should see the piping at least. You won't see the inside of the building. I'll show you the outside of the building. Here is our coal injection. This is the 2 bag houses, the cyclones on the roof. And here's one of the blast furnaces. You can see the furnace with the conveyor belt. Here are the 4 stoves. And the piping bridge for the coal injection was right here. And we have a pipe for each tuer. Now this is what a tuer looks like. This is almost at the bottom of the furnace. You have that big bustle pipe up here. We're feeding air, hot air in here. And we just inject with coal. If you're injecting with natural gas, you do the same thing. Inject it at the tuer. Okay? And for any of you chemistry buffs, I used to be a chemistry buff. I don't know what happened. That's the process. It's a complicated process, but we do a good job. And this is just a slide from coal chemical I threw in to see what it looked like on the overhead. It just goes back into the 2 batteries, the primary coolers, the exhausters, the tar precipitators, and that kind of stuff. And I'm sorry, we have 2 more things to show you. 3 more things. Here are the iron ore pellets. This is iron, and this is slag. How are we doing for time, Judge? Mr. Keith? Only 20 minutes into your presentation. Does anybody have any questions? Yes, sir.
How is it that you remove the slag from the iron?
The slag separates. The slag is lighter and it'll float to the top. So we have a process where we put like a weir. I'm trying to think what they call it. But it's like a weir. And when the iron's coming through the trough and the slag's on top, but actually, I'm sorry, the iron will come out first. Then the slag will come out. And we have what we call a weir that separates that to cause the slag to go through one trough and the iron goes through another trough. So it separates pretty good.
You don't do anything with the slag after it comes out. I mean, you just sell it as...
Yeah. We just sell it. I mean, we analyze it, make sure it's got the right chemistry in it, so we're making good iron. As that has something to do with the way iron's made. If you put a lot of ash in your coal, you'll make more slag. And we're not in the slag making business, we're in the iron making business, so we're going to try and make more iron.
So every bit of the coal gets injected into the blast furnace through the clear?
Yes. And we inject it through the 28 tuer. Yes, sir. Ma'am.
Every bit of the coal gets injected into the blast furnace through the clear.
And we're using, what, 180 pounds on the one and about 240 on the other one. Yes. And we'd like to eventually maybe get up to 300 on each. That was the goal. We're at kind of like at our goals right now, but there's a few other things we have to do to be able to increase our coal injection rate.
How does the blast furnace affect the overall quality of the product?
How does the blast furnace affect the quality of the product? You have 45 minutes. That might be it. Well, we're going to take a break. Does anybody else have any questions? But we have Mr. Keith Jackson here, not the famed ABC Keith Jackson, but the famed Burns Harbor Keith Jackson, and he will beat that to death. Yeah, it's kind of like the coal ovens. We're all customers. You know, maybe you guys, whenever you're going down the line with a mower and I don't like how that blade fits on the mower. Well, the blade people, they screwed me up. You know, you get a little bit of that, but it's all hopefully in good spirit. That's That's a good question. We strive to keep the furnaces lasting as long as possible. We have what we call campaign life. And we will do different things. We might add a little different quality brick because they've come up with a new technology to make a better brick. We've gone to this different type of cooling on this other furnace that we just relined about 4 years ago. Usually about 5 or 6 years. And we'll usually make, about 12 million tons of iron in a campaign life, which is a lot. Well, that's the other thing, too. It can take from anywhere from 50 days to 90 days, depending on what you do and how far down you go in the rebuild. The other thing, too, is when you reline a furnace, you're going to want to use the shell. And if there's anything wrong with the shell, you've got to take extra time to repair that and different things, you know. But usually anywhere from 50 to 90 days. That's the thing you have to look at. It has an impact on our finances, yes. Because we're not making iron, and we're not making iron, we're not making steel, yes. And that's, our next reline is scheduled in '98, and it's scheduled at Burns Harbor. And that's a lot of thought, a lot of thinking going into that. And, you know, it's a big decision. How much do you want to do? What do you want to do? And it's...
What's the impact?
If we're ahead on schedule and we bang the heat to it real well, what's that do? You know, should we take it and go through the right steps? You know, you can do a lot of decisions that can either hurt you or help you. I know it takes a year to rebuild a coke battery. But coke isn't as bad because we can buy coke. Iron is not as available. Thank you. We'll take a 5-minute break, and then we'll listen to steelmaking. Okay.
And what did Bob say in that hour? Ooh, ooh. Basically what Bob said is they take iron ore and they make it liquid. What Bob didn't say, and I know he didn't say it because I listened, is that when they make it liquid, they add carbon to it. Well, I'm going to spend some time explaining how we steel makers take that, or most of that carbon, back out of that iron ore. I want you to feel free to stop me at any time, ask me any questions, okay? I do need to know if there's any metallurgists in the room. Okay, good, because I'm a mechanical engineer. I work in the metallurgical department. They sent me to make this presentation. I can and I will answer all your questions. Had there been a metallurgist in the room, they might have argued with some of my answers. Okay, we'll turn this on and we'll get going. So here we are, leaving the blast furnace, getting ready to board our submarine cars full of hot metal and head over to the BOF. Each submarine car holds about 270 tons of hot metal. And as I said earlier, that 270 tons of hot metal is somewhere around 2,500 degrees. And this is the chemistry right here that we would like to see from the blast furnace. As I said, they put some carbon back into the hot metal, about 4.5%. There's some residual manganese left in it. There's phos in it, way more phos than we steelmakers would like to see, but there's phos in it. Sulfur and silicon. Steelmakers like silicon because silicon produces heat, generates heat. Sulfur is a problem in the finished product, and phos is a problem in the finished product. Phos will generally give us a little more strength in the finished product than what we want, and it's very unpredictable. Sulfur causes many, many surface problems. So as a steel maker, I got to get rid of that carbon, I got to get rid of most of that phos, and I got to get rid of that sulfur. And I'm going to explain how we do that. The first thing that we do in steel making is get rid of the sulfur. We bring the submarine car over, and it comes over on a track, and you can't really see that depicted in this schematic, But we dump the contents of that submarine car into this ladle. And the red part here depicts the hot metal. So we got about 270 tons of hot metal in this ladle. And we inject through a lance, this yellow lance right here that we stick down in the bottom of the ladle, magnesium lime. Somewhere around 1,000 pounds to 1,500 pounds of magnesium lime. Now, after we fill the ladle up, the first thing we do is we take a sample to see what the chemistry is, to see where our sulfur level is, because right now we're trying to get rid of sulfur. So we'll take a sample to see where our sulfur level is at, and depending on where the sulfur level is and what sulfur level we want to get to, that's the amount of mag lime that we inject into the hot metal. Magnesium lime loves sulfur. It floats around in the ladle looking for sulfur, attaches itself to sulfur, and then floats out to the top and forms a slag layer on top. We have a little pulpit right here where this whole process is controlled from, and we had big fume exhaust systems to remove all the waste gases. Here's a picture of the ladle below. The bright stream right here is the submarine car is in the back, and it's dumping its contents into the ladle right now. Here's a picture of an end view of a submarine car tilting and dumping its contents into a ladle down below here. Now, as I said, we inject that mag lime into the ladle. It floats around looking for sulfur, attaches itself to the sulfur, floats out to the top, and forms a slag layer on top of the ladle. And that slag is loaded with sulfur. And hopefully now we don't have any sulfur in the hot metal. So now we got to get that sulfur, or that slag, off of the ladle. And it's kind of a crude process, but what we do is we bring the ladle out this way, tilt the ladle, and the slag is now sitting on top, and we take a rake, and we literally rake all that slag off into a slag pot. And hopefully get rid of the sulfur in the process. And here's a fairly decent picture. You can see the slag. The slag is the dark area right here. The hot metal is the bright stuff in the back. And this is our rake, raking the slag off the top of the ladle. We do lose some iron when we do this. And here's the chemistry. Is this showing up? Can we see this? Because here's the chemistry when we're done. We're same carbon level, same manganese, same phos level, but now we've reduced our sulfur level to where we want it for the customer. Most customers are asking for about a 10 max sulfur, which is about a 0.010. I've got a 0.008 here. The best we can do in this shop is a 005 sulfur. That's about and we don't do that on a consistent basis, but we do have several customers that are looking for a 5 sulfur, and we can get down there. So now I've got the sulfur out, come along with my crane, I pick the ladle up, and I head for my furnace. And if you didn't get anything out of Bob's presentation, the next 2 minutes is all I need you to pay attention to me, because this is the key to steel making. We have 3 furnaces in the shop. Picture one of our furnaces. I brought a scale model of our furnace with me. That's a pretty poor model of a ladle right here. But we bring the hot metal in the ladle from the desulfurization station. We tilt the furnace. We bring the hot metal up. We pour it into the furnace. Got about 270 tons of hot metal in the furnace. We dump about 100,000 pounds or 50 tons of scrap in on top of this, because the blast furnace doesn't always send us enough hot metal, so we have to make up a little bit of it with scrap. Then we take a lance, and for about 15 minutes we blow pure oxygen into the bath. And that pure oxygen combines with that 4.5% carbon that I had up there, forms CO2 gas, and that gas goes out the top of the furnace, and we drive our carbon level down to about a 0.03 to the point where we have steel. And it's just that simple. Did I lose everybody? So here's my furnace. Here's my hot metal. I have a slag layer on top. Slag is very, very important, and it's also a pain in the ass to us steel makers. Now, as Bob said, they make slag over in the blast furnace, and they divert it off. Well, yeah, they divert most of it off, but not all of it off. And Bob says all the phos and all the sulfur goes into the slag. Well, I showed you where we had 70% slag, or sulfur, or 70% phos, and a certain amount of sulfur in there. So we get, from the blast furnace, we get more sulfur, more phos than we want, and some of it comes over to us in slag. And we try to get rid of that slag and keep it down at our desulfurization place. Then when we bring the hot metal up to the furnace, we also, along with the hot metal and the scrap, we dump a whole bunch of limestone into the furnace, about 30,000 pounds of limestone, the same stuff that you would have on a gravel driveway, and we create a slag layer of our own. And slag is very good to us and to the blast furnace because it gives us a place to float out all the things in that steel that we don't want. The trick is keeping the slag in the furnace, or keeping it in the ladle, or keeping it at the blast furnace. And some of us are more successful at that than others. So I got a slag layer on top. I bring my oxygen lance down. I stop it probably about 6 feet above the bath, and as I said, at a rate of 30,000 cubic feet a minute, I blow pure oxygen into that bath for about 15 minutes. And that oxygen, as I said, combines with the carbon, combines with the phos, combines with the manganese, and combines with the silicon, and produces heat and gas. Combines with the carbon and forms a gas and goes out the top. It combines with the phos and forms a liquid and goes into the slag layer. So my slag inside the furnace is loaded with phos. Any sulfur that is left, it will, to a point, oxidize with some of that sulfur and form a liquid and float out into the slag layer. Any silicon in there, we love silicon. It will combine with and it will generate heat. And we have to bring this temperature up. In this whole process, we're generating heat. And we need to bring our temperature up from about the 2,500 degrees we're getting from the blast furnace up to about 3,000 to 3,100 degrees in the furnace. Because when we dump it out into the ladle, we lose some temperature. And then when we process it in our shop, we lose some more temperature. And we have to be about 2,800 degrees when we get to the caster, because if we're any lower than that, it'll start to solidify on us long before we want to. So that's a schematic of our furnace. Here's a fairly decent picture of the crane holding the ladle and dumping the hot metal into the furnace. And it's not a great picture of a furnace, but it is a good picture of them dumping hot metal into a furnace. Here is a picture of the scrap charge. This box up here has got about 100 to 120,000 pounds of scrap in it, and we're dumping scrap into the furnace. Yes?
Compromise the quality of the clean iron when you put scrap into the process. Compromises what you have done before.
We do get hurt to a degree on scrap, mostly on sulfur. Most of the scrap that we charge in our furnaces is about 80% home scrap. That means we produce that scrap here in the plant through various processes. So we know the chemistry of that scrap. It does have some residual metals in it, some copper, some nickel from previous heats that we made that have copper and nickel, but not to the levels that it's going to knock us out of the water as far as making chemistry goes. If there is any excess sulfur, because we have a few high sulfur grades that we do make for certain plate customers, if some of that high sulfur scrap gets back into our furnace, we will get sulfur back out of that scrap and a higher level of sulfur than we want. So there is a minor danger, and we do take that into account. We do have a scrap separation system in the plant where we try to segregate most of the high sulfur scrap. But for the most part, the scrap is fairly clean and it doesn't hurt us. Yes?
Is it required to have scrap steel to make the steel?
No, it is not required. We do have a number of what we refer to as all metal charges, and a lot of times if we're going for a 5 sulfur, a 005 sulfur, rather than take a chance of getting some sulfur back from the scrap, we'll go with an all metal charge and hopefully not get any sulfur back. But yeah, we do have some occasions where we go to all metal charge. If the you know, everything is relative. Sometimes the blast furnace sends you more iron than you want. Sometimes they don't send you enough. You know, so when they're sending us too much iron, we're not going to be charged as much scrap to try and keep up, to try to reduce the iron coming over to us. If our limit is about 130,000 pounds of scrap to a charge, because you add any more scrap, you start losing temperature. The more scrap you add, the more temperature you lose, and it gets really hard to hit that 3,000 degree temperature when you're done. Another picture of us charging scrap into the mouth of the furnace. And then another, and this hopefully is what we'll see today, right here from the observation platform, is this is our #1 furnace right here. There's a man standing right here directing the crane. The furnace itself is a good 30 feet tall. And as I showed in that picture, and in my little bottle right here, we don't even come close to filling that furnace up. I mean, the metal sits in the very bottom of the furnace. Here's a picture of the oxygen lance sitting at the top of the furnace. It's got 4 holes in it that we blow the oxygen through. And again, 30,000 cubic feet a minute, that's screaming when it comes out of there. It makes a lot of noise. And then here's the blow itself. The oxygen lance is lowered in, and then we start blowing. And while we're blowing oxygen, as I said, if you think about it, 4.5% of 270 tons is 20,000 pounds of carbon that's going out the top of that furnace in the form of a gas. So every heat that we make, every 300-ton charge of steel that we produce, we blow about 20,000 pounds of carbon up into our fume exhaust system. Oh, chemistry. As I said, the only thing here is heat, 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 heat. You know, these are all the reactions that I was talking about. The oxygen combining with the silicon, with the phos, with the manganese, and even the sulfur down there. All these reactions are producing heat. When you think of a furnace in conventional terms, you're thinking about burning a fuel. Well, our fuel is in the hot metal. That is basically the fuel that we're using. Now, we know, we like to think we know what we're making. You know, we don't make anything unless we have an order for it. So we know the particular chemistry. This is where we make chemistry, right here. Because once the stuff gets solid again, you're stuck with that chemistry. So we know the chemistry that the blast furnace has sent over to us. And for the most part, it's pretty consistent, but every once in a while you get fluctuations. So we know that's starting, and we know what our end chemistry is going to be. We know how much hot metal we're dealing with. We know how much scrap we're going to charge. We know how much slag or fluxes that we're going to put into the furnace. And all this stuff is read into the computer, and the computer then calculates, okay, this is where you're at, this is where you want to be, this is how long you got to blow oxygen to get to that level. And for the most part, the computer is right. But when we're done blowing for that 15-minute period, we bring our furnace and we tilt it down, which is what I've got right here. You're looking directly into the mouth of the furnace. And a man comes along and stands behind this shield because, again, we're talking about 3,000 degrees right here. And this guy is standing right in front of it. And he sticks a probe in. A little bit of slag comes out every once in a while. He sticks a probe in, he sticks it down into the steel to get a sample. And then he sends that probe to our lab, and within about 5 minutes, our lab analyzes the chemistry, the whole chemistry range of what's in that steel. So the lab then calls back and he tells the individual that's responsible for making this chemistry, he says, okay, here's your carbon, your manganese, your phos, your sulfur level. Here's what you've got. And they also stick a second probe in, and they get a temperature and an oxygen parts per million. As I said, we're blowing pure oxygen in there, and that oxygen is going down into the bath, and it's looking for carbon, and it's looking for manganese, and it's looking for phos. And the more it blows out, the harder it is to find it, because there's less and less in there. So then you start to saturate that bath with pure oxygen. So now you have a certain oxygen level when you're done blowing. And that oxygen is not good, so we got to know where that oxygen level is. So the melter, the guy that's responsible for making this 300-ton heat, gets his information back within about 5 minutes time, and then he decides, okay, is that what I'm looking for? Is that the chemistry I want, or is that close enough? And then he makes a decision. Yes, it's close enough, okay, and then I'm going to put it into a ladle. No, it's not close enough. I got it. My carbon's too high. I got to blow some more oxygen in there, remove some more carbon. My temperature's too hot. I got to put some more fluxes in there to cool it down. Or my temperature's not hot enough. I got to blow some more oxygen in there and get my temperature back up. But the computer, for the most part, is pretty accurate, and it gets us to the temperature and the carbon level that we need, so that, for the most part, we're right where we want to be at this point. Another picture of them taking a sample. Yeah?
Why is it important to remove carbon?
As I said, when the blast furnace senses the hot metal, and Bob left, I hate it when he leaves, senses hot metal with about 4.5% carbon. That's not even cast iron. I mean, that's still got too much carbon in it to be cast iron. You get down to about 2% carbon, then you're talking cast iron, or somewhere around cast iron. When you go down below 2%, you're kind of starting to look at steel now. 2% carbon, 98 or 96% iron. You get down under 1%, now you're talking steel. You get down under 0.5%, 0.5, you're really talking steel. And as you can see here, typically we're a 0.04 carbon shop. We like to refer to ourselves as a 0.04 carbon shop. That's about our limit. We can blow that much carbon out of the hot metal. And when you get down to this carbon level, now you've got steel. That's the best way I can answer that. Yeah.
I know carbon has to be in there for spot welding. You can't have a high carbon for welding.
There's a lot of factors that affect welding and properties and everything, and carbon is certainly one of them. But at this point, we're talking steel now. Now, when you get down to that carbon level, now by definition, it's steel. So we've blown for 20 minutes, and here's our results. We've taken our carbon down to about as low as we can go in the furnace, which is, most of our customers are looking for a 3 to 5. Most of our sheet customers are looking for a 3 to 5 or a 3 to 6 carbon. There's a 0.03 to 0.06 carbon. A lot of our plate customers are up in the into the 12, 0.12 to 0.2 carbon range. We've knocked the manganese out. The manganese oxidizes also along with the carbon. It goes out in the form of a gas. We brought the phos down to an acceptable level. And a lot of our customers are looking for lower phoses. Actually, we don't get the phos this low. We're up around a 0.12 to 0.13 phos level. We haven't affected the sulfur at all. You have to knock the sulfur out before you get to the furnace. You're pretty much stuck with that sulfur level. And as you can see, all the silicon has now left. Silicon is not something that we need in steel, but it's certainly something we need in hot metal to generate heat. And that's our chemistry as we turn down. Now we got to get the steel out of the furnace. And my furnace has got a little hole about 4 inches in diameter in the side of it. Anyway, this is the mouth of the furnace right up here, and this is the little hole that I was talking about. And as we turn the furnace down this way to stick the probe in to take a temperature and everything, we stand it back up, we wait for our test results, we bring a ladle over underneath, and when we decide that where we want to be, we tilt the furnace this way. And as you can see, rather poorly in that diagram up there, but my finger is where the hole would be. All the steel now comes out that hole and into the ladle below. And that's how we remove the steel now from the furnace. Here's a picture of a ladle. The ladle holds about 300 tons of steel. It's probably about 20 feet tall, and it's a good 16 feet in diameter. This is a picture of us tapping steel into the ladle. My furnace is up here. It's actually right now it's tilted towards you. The ladle is down below, and the bright spot here is the steel stream going into the ladle. Now, as I said, slag, we like slag, we hate slag. We put slag in the furnace. We created slag in the furnace in order for most of the phos, which liquefies, to float out into A lot of the excess oxygen has floated out into the slag layer. That slag in the furnace is basically garbage, and we want to keep it there. So we're tapping like this. The slag is much lighter than the steel, so it's floating on top of the steel. We have this thing here, a little bit bigger than a bowling ball, that we call a slag ball. And we drop it into the mouth of the furnace, and the density of the slag ball is such that it is lighter than slag and heavier than steel. So it'll sink in the slag and float on the steel. And as we're tapping, more and more steel is coming out the hole, coming down here. At the point where we start to run out of steel, the slag ball now hits the hole, plugs up the hole, and hopefully keeps most of the slag in the furnace. But it doesn't keep all the slag in the furnace. You're going to lose a certain amount of slag while you're tapping, and then you always, it's a tremendous effort to get every little bit of steel out of that furnace that we can, because there's a lot of money in every pound of steel. So we do get some slag carryover into the ladle, but not a whole lot. That is the, it's difficult for me to say. That's kind of the old way of keeping slag in a furnace. We now have a sensor around our tap hole, which is that little hole in the side, and it senses hot metal. And as long as hot metal is pouring through that sensor, it's happy. But as long as steel is pouring through that hole, it's happy. But as soon as it detects a drop in the amount of flow of steel coming through that hole, an alarm goes off and basically tells the furnace operator. When the furnace operator hears that alarm, he stands it back up. Now that sensor doesn't always work. We don't have it. We have 3 furnaces. We don't have it on all 3 furnaces yet. So we have this system for keeping the slag in the furnace, and we also have a sensor system to keep the slag in the furnace. And it's very important, as I said, for us to keep that slag in the furnace. Yes?
How many balls do you throw in?
One ball per charge. We have 3 furnaces. We strive to make 52 300-ton heats a day. We have 3 furnaces and 2 furnace crews every shift. So we will operate all 3 furnaces in a shift, but in an 8-hour shift, but we don't necessarily have to. Sometimes the crew will stay on that one furnace the whole 8 hours. Other times they might jump back and forth from furnace to furnace. And the whole process of making one heat, it takes time to charge it. It takes 15 minutes to blow at least. You got to wait 5 minutes for your test results. It takes 4 minutes to tap. The whole process itself takes about 45 minutes to an hour to make one 300-ton heat, and we try to do this 52 times a day. Lately, we've been lucky to hit in the 40s. We've been as high as 60 heats a day in our shop. And then when we're done with tapping the furnace, we got all that slag left over, and Bob's got a jar back there of BOF slag. So then we take the furnace the other way and we dump it into the slag pot right here, and we send all that BOF, or basic oxygen furnace slag, back to the sinter plant because it's loaded with iron, and we get the iron back out of it and recharge it in our blast furnace. So we don't waste anything. And as I was saying, that steel is saturated with oxygen. There's a certain amount of oxygen now left over in the steel, and that oxygen is bad. If you can imagine what a glass of pop looks like with all the little carbonated bubbles floating around in the pop, well, that's what oxygen is in steel. It's a bunch of little oxidized bubbles floating around in steel, and if you roll those oxidized bubbles out, and again now we're thinking about a bubble, okay, that's in a slab of steel. If you roll it out in a rolling mill, that little bubble will go like that, and we'll have a big old sliver down in the delivery end of the cold mill. So we have to do what we can to get rid of the oxygen, and to do that we add aluminum, because aluminum loves oxygen. So we throw aluminum into the ladle as we're throwing the steel into the ladle, and the aluminum floats around and looks for oxygen, and it floats out, and it forms a slag layer on top of the ladle. So how do you make steel? You blow on it. Yes?
The silicon content, That's basically removed because of the injection of the oxygen into the...
Yeah, it oxidizes.
Approximately 5 or 6 years ago, we were having a lot of problems in our profile cutting operation, specifically plasma cutting, and it was because of a high silicon content in it. And our people, some of our people worked with your people and reduced that, and it really helped us out a lot. But we never understood what you did to lower the silicon content.
Well, I would have to take a look at your particular chemistry because, as I said, in all of our sheet customers, we use aluminum to remove the oxygen. A lot of our plate customers, and I'm guessing that some of your material is plate material, we use silicon to remove the oxygen. So we do put we have a number of chemistries where we're putting silicon back into the ladle. And I really wasn't too clear on this, but at this point right here, we have this dark thing that you see right here is what we refer to as an alloy chute. And if, as a customer, if you're looking for any particular alloys, if you're looking for a silicon level, if you need copper or nickel in your steel, some people like vanadium or columbium, and all these are strengtheners. If you have a carbon level that's not, where we're looking at for tap, and manganese is a big one. We might add as much as 10,000 pounds of manganese to a heat to get to a manganese level that a customer is looking for. And all of that comes down through these chutes and goes into the ladle while we're tapping. And the tapping process is a fairly violent process. You got this hot metal at 3,000 degrees pouring down into a ladle, and any alloys or anything that you dump in there along with it are going to get mixed in fairly well. So we're making chemistry at this point. We can adjust the chemistry, we can fine-tune it later on in the process, but at this point we're making chemistry because we're not just dealing with carbon and aluminum here. We got a whole bunch of other things. And as I said, I would have to see what chemistry level you're dealing with because we do add silicon back to a lot of our plate grades. And now as to what silicon level you're looking for, you the customer don't always know, and sometimes we have to tell you. And sometimes we have to try and convince you that, well, yeah, we did miss the silicon range that you were looking for on this, but we didn't buy that much, and it'll work for you. But you say, no, we're looking for this range, and that's all we're going to take. So, yeah. All of these additions will affect properties, and most of these additions oxidize. So as there's a certain amount, the aluminum chews up a lot of the oxygen that's in the steel, but manganese will also oxidize. So some of the oxygen will attach itself to the manganese, and that'll float out into the slag, and we don't get all the manganese that we put in there. And when you and we do our best, when you the customer asks for a tight manganese range, we do our best to hit that tight range, but we're not always successful. And as I said, we try to make 52 300-ton heats a day. On average, we miss one chemistry. We miss one chemistry on one 300-ton heat a day. And as I also said, we don't make anything unless we got an order for it. We do not make stock at this plant. One of the biggest complaints about Burns Harbor lately has been our on-time delivery. We are out there knocking ourselves over to make on-time delivery, which means that we do not make anything unless we got an order for it. And then if we miss the chemistry here and there's nothing, and we're pretty well locked in. When we get into the ladle, if we're high, it's hard to take it back out. If we're low, we can always add a little bit more to the ladle, but if we're high, we can't take it back out. So we're kind of locked into the chemistry that we get at tap here. And if we miss that, sometimes we'll call you up on the phone and we'll beg you guys to take it, and as is. And a lot of times you do, but sometimes you don't. And now we got 300 tons of stock sitting out there that we got to find a home for. And we got to go back in and we got to remake your heat. And we do that on average about once a day. That's the chemistry. Okay, so now we're in the ladle. We made some ladle additions. We're pretty close to the carbon and manganese that we wanted. We've kept all the phos in the furnace. We've kept any excess sulfur that was in that slag in the furnace. We've killed the heat which means that we've removed the oxygen by adding aluminum. Now we want to do a couple of things to get this ready to send it to the caster, because the caster is looking for a certain temperature, and if there's any chemistry refinements that we have to make, we have two processes. One is called the degasser, the other is called our ladle treatment station that we can do that at. The first thing I'm going to talk about is the degasser. It has two functions. At furnace, we were going down to a 0.03 carbon. Now don't be confused, we can make any carbon that you're looking for, but basically our furnace, to get to a 0.03, well, to get to a 3,000 degree temperature, which is where we need to be, that's about the carbon level that we're at. Now we can actually knock that carbon level lower. We can go down by a factor of 10 on carbon using the degasser. The degasser either removes carbon or it removes hydrogen. And for a lot of our plate customers, we use the degasser to remove hydrogen because hydrogen causes hydrogen embrittlement, makes the steel very brittle and cracks easily. So for a lot of our plate customers, we run their material through the degasser and it removes hydrogen. For a lot of our sheet customers that are looking for really soft steel, really low yield, low tensile strength material, we send it to the degasser and we take more carbon out because carbon is a strengthener. Carbon adds a tremendous amount of strength to steel. So how do we do that? Well, it's kind of like the furnace in a way. As I said, there's a lot of excess oxygen in that steel, in the ladle, unless you add aluminum. If you add aluminum, it takes that excess oxygen out. Well, to our heats that we want to take more carbon out, we don't add any aluminum to the steel. We leave the oxygen in there. And then we bring it over to the degasser, and now it's got a lot of oxygen in it. It's also got more carbon in it than we want. And what we literally do is we suck that carbon right out of the steel with the degasser. It's a vacuum process. You park the ladle underneath the degasser. You drop it down, these two snorkels, into the ladle. You turn the vacuum process on. You create a pressure difference between these two snorkels so that when you get a pressure difference, you're going to get this kind of action. It's going to want to suck up, and it's literally going to pull the steel out of the ladle up into the degasser chamber, and then it'll fall back down in the ladle. And all this time that and it takes a tremendous amount of force because you have to imagine now, steel's heavy, and you're lifting it with a vacuum up into the chamber, and not only are you lifting the steel, but the carbon is combining with the leftover oxygen in that steel and forming CO and CO2 gas, and the degasser's sucking it out. So with the degasser, we suck the excess carbon and the excess oxygen out of the steel, and we're left with a really low carbon steel. And that's how we remove carbon. Now if you just want to remove hydrogen, you go ahead and you kill the steel. You add aluminum to it, you remove all the excess oxygen, and now that carbon has got nothing to combine with. It doesn't have any oxygen in there, so it stays with the steel, and all you wind up sucking out is just hydrogen. And let me jump ahead here to my chemistry. Down at the bottom, you can see we've gone from a 0.03 carbon in the furnace down to a 003 carbon at the degasser. So, and we have not affected the phos, the manganese, the sulfur, the silicon, or the aluminum at all. We've basically just sucked all the carbon out with the degasser. And this is a fairly good picture right here of the degasser sitting in a ladle of steel. It's a very boring process. I mean, you just set it down in there and you wait 20 minutes while all the action goes on inside the degasser, inside the degasser chamber. Any questions on that? So if we don't send it to the degasser, if we don't need to remove any more carbon, we'll send the steel to what we refer to as our ladle treatment station. I think this diagram is in your book, but I got my ladle of steel sitting on a ladle car, and again I have 300 tons of steel in here, and now I'm somewhere around 2,900 degrees. And the caster has called us up and said, all right, I need this heat at 10:15, and I need it at 2,800 degrees. So the guy that's sitting in this pulpit right here I have an operator sitting in this pulpit, and I have a metallurgical individual that's sitting in this pulpit. And the metallurgical person is responsible for the chemistry. And I wasn't as clear as I could have been, but when, way back, when we're in the furnace and we tilt it down, we get a sample to see what chemistry we're at, and we're happy with that. We stand it back up, we put it in the ladle. Well, after we put it in the ladle, we take another sample, and we send that sample to the lab. And the lab then sends that information back to the computer, and everybody's got a computer screen out there. And all these sample results will follow that particular heat of steel through the process, so that the people that are responsible for that one, because after it's left the furnace, the furnace crew stays where they're at and they start working on the next one, and then a new group of people pick that heat up and follow it through the shop, and they are now responsible for making chemistry and getting the right temperature. And those sample results, and they are not limited to just one sample. We probably take 6 or 7 samples on each heat as through the process. And every time we make, well, not every time we make an addition, but we'll take one before we start, and then as we are getting ready to send it to the caster, we'll take a final sample just to make sure that we're close to where we needed to be. So anyway, the metallurgical person working with an operator in here knows the chemistry that he's got. He knows the chemistry that he's trying to make, and he knows the temperature that he wants to be at. And we can affect temperature 2 ways. If the steel's too hot, if the caster needs it in 20 minutes, and you lose a certain amount of temperature, just the atmosphere, but if you're not going to lose enough, we can add scrap metal to the steel. And the way we do that is, you know, I'm going to pour this back into the ladle, but now I got my ladle full, okay? We'll just dump a whole bunch of scrap back in, and we'll take our lance and we'll stick it down in, all the way down to the bottom, and then we do basically the same thing. We blow again, and that blowing action, and we use argon at this point, that blowing action will just mix everything up into the ladle, and it'll melt the scrap, and it'll cool the steel down to the temperature that we need. If the steel's too cold, we need to add temperature to it, we will stick an oxygen lance down into the steel. We will add oxygen and aluminum to the steel, and we will create heat through that process, because the oxygen, as I said, and aluminum, they get along really well, but they also produce heat, and we can add temperature back to the ladle. But also at this point, we will add any other alloys from our alloy bins up here that we need to add to get to the chemistry that we want. If we're off a little bit on carbon, if we're off a little bit on manganese, we can add some carbon and manganese back to it. I'm running out of time, so I'm skipping through these. What I did want to show you here is at the ladle treatment station, a lot of the alloys that we add are in bulk. They're in bags. We just drop them down through a chute, drop them onto the ladle, or into the ladle, and we mix them in. Some of the alloys that we have carbon, aluminum, titanium, and calcium silicon wire. And it's in the form of this is a spool of wire down here, and it's about 3/4 of an inch thick wire that will feed down into the ladle and will drive the alloy into the ladle using wire. And that's another fairly decent picture of the wire feeder. And then this is a view from the bottom of the ladle treatment station. Again, this is the ladle right here, and they've got probably what they're doing right now is reheating, which means that he's got his oxygen lance in there, he's adding aluminum to it, and it is a fairly violent process, and it does kind of spit every once in a while stuff out of the ladle. And at this point now, we're locked into our chemistry. We take a sample, we're locked into our temperature, there's not a lot more we can do with it. We're locked into our chemistry. We're pretty happy with our chemistry, and at this point, we're ready to make it, take this liquid steel and make it hard. Any questions up to this point? Okay, now I got to get this steel out of my ladle. And what we're looking at here is the bottom of the ladle, and this is my tap hole in the ladle. I got a little, actually it's a little 4-inch hole sitting in the bottom of the ladle, and there's a slide gate on there, that a gate that literally slides shut, and it's obviously shut all the time while we're working on it. And when we get over to the caster, or if we're going to make ingots, the gate, we get the ladle in position, and we just basically open it up. but that's a fairly decent picture right there of the hole in the bottom of the ladle. We have 25 ladles in the shop. And at any one time, we're probably using 7 of them. And as I said, we're losing temperature when we take the steel out of the furnace, we put it in the ladle. We're losing temperature as we're moving the ladle around the shop. If we're not using a ladle, it's very important for us to keep it warm, to keep it hot. Because if I pour steel into a cold ladle, I'm going to lose an awful lot more temperature. So I have heaters, and that's what this ladle right here is sitting on a heater right now, staying warm. So the ladles that we're not using and that we're not repairing, we got them on a heater, and we're keeping them warm. What the hell is that? And that's not a very good picture either, but this one's better. We have 2 casters, and 80 to 85% of the stuff that we make we send through our casters, but the other 15 to 20% we'll pour in the form of ingots. And this is a fairly decent picture of the top of several ingots that are full of steel. And the ingot right there probably weighs about 60,000 pounds. So we can fill up anywhere from 8 to 10 ingots from every 300-ton ladle. And this individual right here is doing, right now, what he's doing is he's taking a hydrogen sample. He's seeing how much hydrogen is in that ingot right now. As I said, the plate mill does not like hydrogen, and we can measure that level. We have 2 different ways of pouring ingots. And this would be so much nicer, wouldn't it, Bob, if the room was darker? Yeah. We can either park the ladle over the top of the ingot, open up the hole, and pour the steel into the ingot. And as you can imagine, that steel's coming down, it's splashing all over the sidewall of the ingot and filling the ingot up. And you're going to wind up with not your best product. We don't send any ingots to our sheet customers, only to the plate guys. But they order it that way. Or we have what's known as bottom pouring. And I've got 4 rather large ingots sitting here surrounding this trumpet. And what we'll do is we'll come and we'll park the ladle on top of this trumpet. We'll open the slide gate, and the steel will flow down through this trumpet, through troughs in the ground, and it'll fill the ingot up from the bottom. This is what we refer to as bottom pouring. Much, much cleaner way of making ingots. And here is another pour picture of the steel in solid form being removed from its ingot shell. And that's a great picture right there of the same process. It's still hot when we're taking it out of the ingot mold. And now we have an ingot of steel, and we need to roll it into a slab form to either send it to our hot mill or a plate mill. So what we do is we have to send them over to the slab mill, put them in furnaces, heat them back up to about 2,300 degrees, and then roll them through our slab mill out into slab form. We don't like to do this. It's real expensive. The quality is not not the best, but a lot of our plate customers are ordering chemistries that we cannot cast, and a lot of our plate customers are ordering slab or plate thicknesses that we cannot roll into. We can't roll into. Our caster slabs are not thick enough that we can roll into the plates that they need. So we do make ingots here in the shop. But what we're really proud of is our caster. We have 2 casters. One was built in '76. The other was built in '83. Basically, your 300-ton ingot comes over to the caster. It empties the steel out into a tundish, which is kind of just like a holding chamber. A tundish is about the size of one of the tables that you're sitting at. At both ends of the tundish are nozzles that open up into a mold. The steel flows out of the ladle into the tundish, out of the tundish into the mold, and in the mold it forms the slab that we're talking about, and then it just follows a series of rolls down through the caster and comes out the other end in slab form. It's another picture of, I was really hoping this picture would be better, but it's a picture of our caster, Here's the ladle with its 300 tons of steel. Here's the ton dish, and the ton dish holds about 100,000 pounds of steel. And down below the ton dish, where these men are, is the mold, and that's a little better. We will see the caster, one of the casters today in operation. Here's a fairly decent picture of a ton dish. And again, as I said, the ton dish is about the size of this table right here. And at either end of the ton dish is a nozzle that the steel comes out of. So it flows out, the steel comes out of the ladle, flows basically into the center of the ton dish, and fills the ton dish up. And then it flows out of either end of the ton dish and into the mold. And the purpose of the ton dish is, a caster is a continuous process. We want to keep this thing going all the time, but the ladles empty out. We run out of steel in a ladle, and we got to bring a new ladle in. So when you start off, you bring your ladle in, you fill your ton dish up, and then you open your molds up, and then you coordinate your speed from that point on. The amount of steel coming out of the ton dish is the same as the amount of steel coming out of the ladle, and you match those speeds all the way down. Now your ladle empties out. Well, you still got your ton dish full of steel. So basically, you just keep casting with a full ton dish, and you get your ladle out of the way and a new ladle back into position, and you open it up, fill your ton dish back up, or anything that's drained out of the ton dish at that point, and you basically you haven't missed a beat. You're still casting. There's a man standing in a ton dish. This is a picture, as I said, at either end of the ton dish, we have a nozzle that comes out of the ton dish and goes into the mold. This is a picture of one of our nozzles. A ton dish will last about 9 to 10 ladles. After 9 to 10 ladles, after you empty 9 to 10 ladles into a ton dish, you've pretty much eaten the inside of that ton dish out. You got to get it out of the way and get a new ton dish in and then rebuild that ton dish. These nozzles right here at either end of the ton dish, they last about 2 ladles. And we're looking at $750 right there. So every 2 ladles of steel, I'm replacing 1 or 2 nozzles at $750 a piece. Yeah.
If the ton dish has a constant dripping action, for layman's terms, how do you get in and replace the nozzle?
Good question. Let's jump ahead. Well, there was a picture of a nozzle. Let me jump ahead just a tad more here. Okay, I'm going to have to back up because that's the only place that I have it. See this little bright spot right there? That's where the mold is, and this thing right here is the nozzle coming out of the bottom of the ton dish. We replace nozzles while we're casting, and we continue to cast while we replace the nozzle. And what we do is our caster runs about 40 to 50 inches a minute. And we could slow that caster down to about 10 inches a minute. And when we do that, you got your ladle sitting on top of your ton dish. You raise your ton dish, you raise your whole ton dish and your ladle up out of the mold. The nozzle comes up out of the mold. You pull the nozzle off, slide a new nozzle on, lower the ton dish back down into the mold, and all that takes less than a minute, and you continue casting. And then you bring your speed back up and continue casting. So there's a number of things, like I said, the ton dish is there, the mold is there to keep you casting, to keep you from turning around. All the action happens inside the mold. The mold is 10 inches thick. It's only 40 inches deep, and it's whatever width you, the customer, are looking for. We can change the mold size, mold width from about 40 inches out to about 75 inches. And if the hot mill is ordering a 50-inch slab, we can either send them a 49 or a 51-inch slab, and they can roll it into a 50-inch slab, but we can't send them anything any wider or any narrower than that. So your ton dish is sitting up here. The steel is coming down through the nozzle, and again, there's a nozzle on either end of the ton dish, so I got 2 molds down there, and we're making 2 bars of steel. And the steel comes in, and it basically fills the mold up, And again, the mold is only 40 inches deep from my hand down to the floor. So during the time, and we're moving at 40 to 50 inches a minute, so we're in the mold less than a minute. It's a continuous process. Steel continually flows down, and as it leaves the tundish, it goes into the mold, it starts to solidify, and by the time it comes out of the mold, it's got a solid shell with a candy-coated inside, okay? I got a solid shell here at the mold wall all the way around, and I got liquid steel in the middle coming out of the mold. And as I come out of the mold, now I'm looking up into my mold face right here, and I can see the 10-inch thick wall. I got a series of rolls that guide the bar all the way down. And there's water sprays in here while we're casting, so they're constantly cooling the slab as it's coming down, and as the slab is coming down, the center is solidifying. So by the time we get down to the bottom, we now have a solid steel bar. But when I come out of that mold, we are not solid. It's still liquid steel inside. Here's a fairly decent picture of the top of a mold, 10 inches thick, 40 inches deep, and whatever width, as I said, I can vary the width anywhere from 40 inches to 75 inches wide. So now I'm looking at the bottom end of the caster here, and again, I got a nozzle at either end of the tundish, so I got two slabs coming out of my caster, and at 40 to 50 inches a minute, I can empty a 300-ton ladle in about 40 to 45 minutes of steel. And we try to, through our number 2 caster, which is our plate caster, which is our strip caster, we try to run anywhere from 28 to 30 cast heats a day and keep that caster going all the time. And the big thing about casting is most of our strip grades are compatible, if you will, chemistry-wise. You got to remember that 300-ton ladle has got a chemistry of its own. And I bring in a new 300-ton ladle, the chemistry of it might be for another customer, and it might be slightly different. So I'm going to get a steel mix inside my tundish because I am constantly pouring steel. So we might lose a couple of slabs in the process, those 2 slabs coming out of either end where I had the chemistry mix. I'm going to have to get a drink of my steel here in a minute. Excuse me. I have now got a chemistry mix, and it's not the chemistry that you, the customer, are looking for, but we do have other customers out there that will accept that chemistry. So we might lose a couple of slabs here and there through the process, but it's very important for us to keep going all the time. If we lose a strand for one reason or another and we have to shut the caster down, it takes us 90 minutes to get it started again. And we're making steel back behind that. We are constantly making steel, and we are making steel for the caster for 11 o'clock, for 11:30, you know, and if all of a sudden the caster goes down and says, I don't want that steel anymore because I got to turn around, well, we've already made it. Now we got to do something else with it. We got to find some ingots. We got to change the chemistry, see what, you know, other orders out there that we can make for it. So we get very upset when the caster goes down. We try to keep our caster going all the time. Over on our number 1 caster, it's a little bit different. We run a lot of vanilla grades on our number 2 caster. On our number 1 caster, we're making a lot of special type stuff. It's more of a plate caster than a strip caster. We're making a lot of special chemistries there, and we don't have the luxury of mixing the chemistries. So if we get a real wide chemistry range, we'll literally have to shut that caster down, turn it around, empty it out, get it started again, and come in with a new chemistry, which is time consuming, and it's also very costly to us. So I got this continuous slab coming out of my caster, and now I got to cut it up to the size that you guys need for your coils or plates. So I got a couple of torch machines on either slab and again the slab's moving at about 40 inches a minute. The torch machine follows the slab along, and as it's following it, I got torches on either end, and they're coming in and they're cutting as they're moving, and we're cutting the slab to the size that we want. And there's a picture of a couple of slabs, or both strands coming out, another picture of both strands, and you can see the one torch machine is cutting here, the other one is off the strand. The bottom end of our number 2 caster, going good picture of a slab right there coming out. The bottom end of our number 1 caster, slab coming out of it. And then we get the slabs down at the end. We have a computer that tracks the whole process. It tracks every inch of every slab that we make. It'll assign a number to each slab, and each number is unique. And we take these, and the computer prints out a little metal tag for us, and we nail the tag into each slab to identify it. So any problems that you guys have with history or anything, that you call up our salesman and say, hey, listen, this stuff just isn't working right. What did you send me? And say, well, give us a sample and we'll see what it is. So we'll get that sample from you, we'll analyze it, we'll track it all the way back to our furnace, and we'll see what, we can see what we did here at the furnace if that's where the problem originated. So we have that ability to keep an eye on the stuff. Then we come in with a crane, and our crane has got 4 slabs right here, 1, 2, 3, 4, picks them up, brings them out, sets them down, and this is a picture of a slab hauler. Whoops, last picture. Picture of a slab hauler that picks that slab up and carries it away to either the plate mill or the hot mill. Now, take a good look at that slab. There's no roll marks, no rust, no pickle stain. That is a quality product when it leaves steel making. Now the hot mill will come in here this afternoon and tell you how they screw things up. Any questions? Yeah.
Keith, could you clarify for me again the ingot process versus the cast process for plate? I mean, do you develop plate from ingots based on size or based on chemistry?
Both. It's probably more so chemistry than size. There's probably a very few sizes of plate that we make where we actually cannot cast them, but there's a lot of chemistries out there that the caster you just can't cast. As you're coming down through that process, as I said, you're liquid in the middle, and as steel solidifies, it tends to solidify out toward the edge and perhaps leave a little gap in the middle. And depending on what the chemistry of that grade is, that gap can really expand, and you wind up with cracking or splitting or some kind of segregation. And there's a lot of chemistries that just happens more on than others, and we just can't cast those chemistries. So we make plate. Yeah.
On the vacuum to gas, what's the limitation as far as tons or percentage of the metal to the gas?
I'm gonna struggle with this question because I know I'm not going to answer what you're asking. The process itself takes about 20 minutes. Our degasser is, I want to say we do about, I told you I'm not going to answer this question. And I told you I could also answer any question there was. We're making 50 heats a day in the furnace, which is about 350 a week in the furnaces. Our degasser, we're lucky to get 80 heats through our degasser a week. It's a very deteriorating process. It's hard on the whole process. After a certain number of heats, you got to shut it down. You got to clean the inside out. The brick only lasts a certain amount of heats. You get buildup in the elbow coming out of the vacuum itself. It's just very difficult for us to push more than 50 to 70 heats through that degasser a week. Some of our competitors are very good at pushing 50 heats a day through their degasser. We're just trying to do different things in our degasser than they are, and we're not as successful, I guess. Does that even come close to answering your question? It does? Okay, good. Any other questions? Okay.
My name is Karen Reefy, as it says in your schedule. I am a process engineer in the Quality Assurance Department in the hot strip mill. I've been with the company almost 4 years. I've been in the hot mill for 2 of those years. So I'm starting to get to know my way around, but I may forget a few things and don't know everything yet. So I will do my best. This is the first class of the year. I am a little rusty from over the winter, so just bear with me, and please feel free to ask questions if I miss something or you don't understand anything. I will do my best. Well, the first slide I have for you is who are the hot mill's customers? And I like to call it the cake chart. I don't like pie, so I made it look like a cake. 50% of the product we make in the hot mill goes to our cold mill. We are getting heavily into the automotive industry, and so that's where we're putting a lot of our product. 30% it goes out the door, just as what we call black bands or hot bands. And the final 20% are hot mill product, like hot roll pickle or temper pass, cut to length, those type of products. So I'm going to take you up to here. I will touch briefly on some of our hot mill products, but we'll go through the hot mill to get a hot band today. Some examples of where our material goes. Some of these apply right here in the room. Automotive and truck frames, such as the material we ship to A.O. Smith. We have automotive wheel rooms. Bessie in the back of the room is familiar with that one. Hot water heaters, lawn mowers, all sorts of good stuff. Steel is everywhere. You don't really think about where it is, but my desk, my chair, my car, it's a big industry. Now the next slide, I think this is in your book, looks something like this. I don't like this picture very much. I made one of my own, and hopefully I will get this one inserted into the book. But here's the beginning of the hot mill. Kind of a flow chart of how the material from the caster gets out the door as a coil. The first step is the slab yard, where all the slabs from the caster end up. We have 3 pusher furnaces, and I'll talk about all these in detail coming up. Slab comes out of the furnace, goes through a vertical scale breaker. Through our roughing mills, we have 5 through 7 finishing stands, and then to the coiler. And from here to here, through the yellow area, is 3 to 4 minutes. So it's very, very quick once we get the slab out of the furnace. And then goes through a series of conveyors and scales, and from there it gets sent on its way. We have 2 storage areas. It's actually one big building kind of separated into 2 areas. Raw coil storage for the cold mill, and then our hot coil storage where we send coils to our slitter. We do slit product. We use this line mostly as a reclamation line. Our combination line, which is temper pass and cut to length. Our temper mill, which is just a temper pass line. And then we also have shipping areas for all of these, and then a 4th one for just black bands. So that's how things move. Let's talk about the hot end of the hot mill. This is where our tour will start. We will come in through a door approximately here by our furnaces. When the slabs come over from the caster, I don't know if you got to see one of our slab haulers, but they bring them over in those big piles. They sort them out in a building kind of over there on this slide, and they get lined up into our 3 furnaces. We have pusher furnaces, which means when you push one slab in the back, one falls out the front, and we push them in 1, 2, 3, 1, 2, 3, nice orderly manner. I have another picture of the furnace so you can kind of understand what it looks like. It's shown as a box here just to make things simpler. Our roll line is on the front of the furnace here. The vertical scale breaker, which I mentioned, and here are 5 roughing stands. This area of the mill is very, very long, and I'll explain that in a minute. It's the mill itself is well over a quarter of a mile, so you're going to be walking a lot, but there aren't as many stairs as this morning. But first, I'll just show you what the furnaces are like. Here is a cross-section of one of our reheat furnaces. The material is flowing this way, as shown by the arrow. This is the back end where we push the slabs in. These furnaces have 5 reheat zones, the top and bottom in the preheat zone, top and bottom in the heat zone, and then one area here in the soak zone. This area of the furnace is 2100 degrees, and these 2 areas are 2300 degrees, and that's to make sure that all the microalloying elements are fully back into solution in the slabs. Some dimensions are given here. The furnaces are 105 feet long and 34 feet wide, and we could get about 600 tons of steel in each one. And then the number of slabs depends on how wide and how long they are, but the maximum length is about 380 inches. They could squeeze 384 if they're very careful, but if we get one cocked in there, it could get stuck. So we have to be very careful. Let's see. Let me get my notes, make sure I'm not forgetting anything. Make sure you guys get it all. Nope, that's about it. Time. It's a constant push. Takes about, I would say on the average, 2.5 hours to get from here to falling out here. When we push one slab in, one comes out down this, well, it's labeled the dropout skids, across this apron and under a roll line. And these are bumpers here to catch it as it falls this way. The distance from here to here is 8 feet. So it's a little rough, and hopefully they'll be pushing when we get there. We usually get to the mill right after shift change, so hopefully they'll start it up when we get there and you'll be able to see these slabs come out. It's quite an event. And just this is a better picture of what you'll see. To be able to visualize it, we'll walk across the line here on a walkway over the roll line, and the floor level is right about here. And then we'll walk along here. Here's where the slabs drop out, down the skids and onto the roll line, and then head this way.
Why could the slab go directly from the continuous caster directly into the hot mill?
In the reheat furnaces, they can.
The furnaces, it seems like they're already hot.
Well, they are, but they're not hot enough. We do have to make sure they are at 2300 degrees when we start, because there's a lot of cooling before you get to the finishing stands. We have to make sure that the slabs are above the austenite ferrite transformation temperature before we get them to gauge. Otherwise, we'll end up with brittle.
What are they
Stone cold
when they go
into the furnace. We have what's called cast direct, where we'll take slabs directly from the caster. When they push them off into those piles, we'll bring them right on over and stick them in. I don't know what that temperature is, to cold right off the floor, and that's why they're in there for such a long time, to make sure we do get them to 2300 degrees. We would like to hot charge as much as we can, but sometimes the caster schedules don't meet up with the hot mill schedule, so we have to put them on the ground for a few days. Now, I buried the one that I need. So that was the furnaces. The next step is the vertical scale breaker. There is a break in the picture here. Between the furnaces and the vertical scale breaker is a scale. We weigh every slab before it starts the process, and we also check the width. Just one last check to make sure the mill setups are correct. The vertical scale breaker, affectionately known as the VSB, is something like this. 2 drum rolls with like knuckles on them. and they squeeze the slab about 0.5% to break the scale jacket off, like getting paint to peel off your house. It gets the scale to break off, and then 2100 psi water to blow the scale off, so that we end up with as clean a slab as possible before we start rolling it, because we don't want to roll the scale in. We are continuously taking the scale off as we move down the roll line, because the slab is at that temperature is always reoxidizing over and over again. So there's a lot of water and a lot of scale flying around.
What do you call it? Is that what you mean? Pickle? Is that what pickle was the first?
Pickles, same type of thing. Just pickling is removing that real thin layer of surface scale off of the band, as which forms when it's cooling. This is real thick, heavy, chunky stuff that forms in the furnaces.
What's the water that you use? I can understand.
2100 psi, 2000 psi, 2 ksi water. Yeah, 2100 psi. So it's loud and it's hot, but it won't be wet where we are. We'll be up on a catwalk. So. The next step are the 5 roughing stands. We do not have an edger in front of R1, roughing stand 1, R1. We have the vertical scale breaker, but in front of R2, 3, 4, and 5, we have what's called the vertical edger. The width of the coil, the final width of the coil, is established when it comes out of this 5th stand. And we can squeeze or spread a slab on the average an inch. So if the caster is off a little bit, we can squeeze it out or bring it in to make sure the width is correct. This is a rough picture, but it does have some interesting dimensions on it. All the slabs coming out of the caster are 10 inches. We get it to 1 1/4 by the time we get through the 5th stand. And here are the dimensions of the slabs as they come out of each stand. We'll take it down to 7.7 inches out of the first, 5.5 to 3.3 to 2.2 to 1 1/4 inches. When the slab drops out of the furnace at 2300, it's still about 1900 to 2000 degrees here. And we will be standing on an overhead walkway right around here. So the heat does rise and it will be very hot. So don't feel too bad about unbuttoning your coat, taking your gloves off or whatever, because it is quite warm in there.
Looking at they refer to the thickness?
Thickness, 10 inches to 7, 5.5, down to 1 1/4. And just this is a pretty simplistic picture of what our vertical edgers do. Set the width before it goes through the stand. Now I said we have 5 roughing mill stands. The first 2 are what are called 2 highs, and the last 3 are 4 highs. And this is what we mean by them. R1 and R2 look like this. The floor level is right about here. So there's a lot of it that's in the basement. But there are no backup rolls on these 2 stands. Versus a 4 high stand, which has backup rolls to reinforce the work rolls, to make sure the work rolls don't deflect when they're trying to take it down to that final dimension, down to 1 1/4 inches. Just some, for people who like dimensions, I know some people like numbers. The work rolls in this here are somewhere between 43 and 48 inches in diameter, about this big in diameter. The backup rolls here are 60.5 inches in diameter, and the work rolls are 41 to 44.5 inches. So this is a very large equipment. Again, the floor level is about here. We have to take 4 plates out to change these rolls out on the weekends. I've never been out on a weekend. I'd like to come out on a weekend and watch them do that. many people have been through these overheads. I have 5 sets of notes in here. Okay. This is the last time we'll look at this slide. Through the furnace, 2300 degrees, pop the scale off, and then knock it down to 1.25 inches by the ordered width, and at about 2000 degrees. And that's a couple minutes. But now we start getting serious. This is the finishing train. Between the last roughing mill stand and this area here where our crop shear and the pinch roll scale breaker is what we call our delay table. We do get orders once in a while for 1.25 inch plate off the hot mill, and we do sell that product. That's also an area where if something happens upstream, we can push slabs out of the way. So it gives us a chance to get things cleaned up. The slab can go cold if we have to wait too long. So that's an area where we can push things off to the side and get ready to start up again. If something is pushed off to the side, it will not be used in the hot mill. We'll cut it up and take it back to the BOF to scrap, or maybe find a buyer for it. The finishing stand basically starts here with a crop shear. There's also a width gauge at this area. The crop shear has an electric eye that looks at the head and tail end of the slab, and the computer figures out just how much of a crop it needs to take to get rid of any fishtail or variations in the ends of the strip. It's very important on the head end that it have a flat edge coming in so that it feeds in straight into the mill and doesn't get turned one way or the other as it feeds through the finishing stands. So you'll see it's a rotary crop shear. So you'll see it come on and turn, and then the crop fall into the basement, into a bucket that are later cleaned out. You should be able to see, if you're not afraid to look over the railing on our way by, you'll see the crops in railroad cars getting ready to be taken back to our BOF. Or to Laurie Brothers, I'm not sure where they go. We have a pinch roll scale breaker, one more chance to get the scale off. I'm not sure what the water pressure is there, but 2,000 psi. The next step are the 7 finishing stands. There are edge guides there, but nothing is done to change the width. Basically, we're just getting it down to the ordered gauge within these 7 stands. The 7th stand is basically used for finish, surface finish, and a general shape. It shouldn't, under normal circumstances, shouldn't be used to affect gauge. We do the gauge through the first 6, and the 7th is just to ensure flatness. These stands here are 18 feet apart versus R1, 2, 3, 4, and 5, which are far enough apart that the slab can sit in between them. It is only in one roughing stand at a time, and basically that's to give the slab a chance to redeem itself. There's a lot of work being done, just kind of a little stress relieving step there. That's one of the reasons why the mill is so long. If you think about a 380-inch slab, 10 inches thick, being reduced to 1.25 inches, if you think how long that is, I used to have that written down. 600 and some feet? You gotta have enough room for that slab to sit out there and cool if need be. But these are all right in quick succession. They're 4 high stands. Let me don't get, I'm gonna get ahead of myself here. Let's see. Oh yeah, here's some interesting things. We do automatic roll changes. If we do a general roll changes, which we change all 7 stands at the same time, we can do all of them in about 10 minutes. It's kind of like a pit stop at Indy out there. The speed coming out of this stand here is about 30 miles an hour. Depends. Now if we're doing what we call a coiler schedule, which is heavy gauge, like for Deere or like Owen Industries, that's running a little slower. But this is where I get to my plug-in about rolling schedules. Sometimes a customer will call up and say, oh, we need steel right away. The thing is that our schedules are set up days ahead of time. Our schedules are based on a width. We start wide and go narrow as the week goes on, just like the caster does. And the schedules are set up on footage. We try to change these rolls out after a certain number of feet. So if we're doing like a light gauge schedule for the cold mill, we're changing out the rolls more frequently. Whereas if we're doing, heavier gauge hot roll, we don't have as many generals to do in a day. And I will talk about these also. We have some X-ray gauges here in our runout table where our cooling sprays are. I'll talk about those in a minute. If you think this picture looks familiar, it is, because all of our finishing stands are 4 highs, just like the roughing stands 3, 4, and 5 are. And again, the floor is right about here. And if it isn't intuitively obvious, this is the way the backup and the work rolls function against the slab as it's traveling in this direction. And there's just some verbiage there about how that works on that page. Well, before I take that down, on this page I talk about our gauge control in the hot mill. And it's easiest if I have this picture up to explain. We have 3 methods of gauge control in the hot mill. And we're working on a 4th. The first component of our gauge control, and this gets kind of confusing, is what we call an X-ray monitor control, which is a closed loop system, which tries to maintain the aim gauge off the last stand, of the last finishing stand, and feed it back. So it's looking at the aim gauge from here and feeds that information back to this one, and this one back to this one, and back and back and back. And there's a feed, that one's going backwards. Then there's a feed forward system, which is a predictive system, which measures the roll force in here and feeds that forward to the other 6. And then the third, a gauge meter gauge control, which maintains a constant exit gauge for each stand based on the roll force. So we've got one going backwards, one going frontwards, and one that's looking at all 7 all at the same time. And we have a new system going in. We just put new hydraulic loopers on these 3 stands, and the computer system to go with that is being installed this year. Yeah, that was dry, but it's part of the presentation. Okay, what does a rolling stand look like? Well, that's what the slab sees, so you can only imagine. You're going to fit through there, all right? Oh.
Karen, the gauge reduction does not increase the width of the steel, just the length of the steel.
We have edge guides to make sure the steel doesn't squeeze out anymore. Yeah, we set it when we come out it's set when we come out of those roughing stands. There's some dimensions on this page. Again, equipment's pretty big. The maximum, these backup rolls here can be 60 inches in diameter. And these work rolls are much smaller than the roughing mill stands. These are only about 28 inches. So that's to this point. We have an 1 1/4 slab about 1900 degrees coming out of our 5. Comes through the crop shear and gets the head and tail ends cut off, through another scale breaker, and then through the 7 finishing stands where it is reduced to the ordered gauge and is at ordered width. By here, when it gets to here, it is still above the steel's transformation temperature, which is based on chemistry for the most part. The Met department that I'm in, we set those temperatures, which my average is 1600 degrees. So even with all this water and work being done here, you only lose about 300 degrees. Next we have some x-ray gauges. We have a stationary centerline x-ray gauge, a traveling x-ray gauge that moves across the strip to give us a profile. We can guarantee profile out to within 2 inches of the strip. With our new equipment, we'd like to move that out to 1 inch or even further. We'll try. And we also have another width gauge on the outside. We have one here and here. The next section of the mill is what we call the runout table. We have 10 banks of sprays that we can turn off if we need to. There's a computer model for every chemistry that we run on the mill that it knows if the Met department said to cool it to this temperature, it knows how much water to turn on. There are sprays from the top and the bottom. And this is what one of those banks looks like. Is that right? Yep. This is the strip here moving in this direction. The runout table itself is, it says 500 feet long here. I thought it was shorter than that. The top sprays could put out 45,000 gallons per minute, and the bottom sprays can shoot up 15,000 gallons per minute. All of our water we pull in from Lake Michigan. We have cooling ponds across US 12 here, and then we put it back just as clean as it was before. All it does is touch steel and a few degrees warmer, so the fishing out where our outlet is pretty good from what I hear. I don't fish myself. The runout table is not long enough to do intermittent cooling for dual phase materials, so we can only do single phase materials. And the purpose of controlling the water closely is that this is a step where we establish the final grain size of the steel, which then determines the physical properties and the drawability. We reject coils if we don't hit the temperature range, which is about 75 degrees wide. And we're very successful at hitting our temperatures. Lately, the hot mill has established some, not, I guess you could say quality teams, but work teams, and one of them is devoted to coiling temperature control. So they've been studying this very carefully, and we've been making some good improvements. Most steel, just a metallurgical phenomena, steel, when it's going through its transformation from austenite to ferrite, gives off heat here. So as we're putting more and more water in the strip is actually trying to give off heat. We do roll some steels on our hot mill that do not give off heat, and it really gives our computer a headache. That's why we have the capability to manually override, because we were having problems like, what's going on? And then we figured out that the steel isn't like every other steel, and so we can turn the water off if we have to, or turn it on if something were to happen to our computer system. So. Well, I think you probably heard me say earlier, I was talking about the last finishing stand, the steel's going about 30 miles an hour. So, okay, it's going 30 miles an hour now. What are you going to do? There are these really big catcher's mitts down at the end of the roll line. We have 3 coilers. They're called down coilers. They coil in the belly down position. Let's see. I have to get this straight. The operators will get me if I don't get this right. The strip is coming along here, goes through this pinch roll assembly, is caught by this wrapper roll. One lap gets wrapped around the mandrel, 1 or 2, and then all the rolls release, and the mandrel takes over and coils it up. Going 30 miles an hour. So, then a buggy comes in, takes the coil off of the mandrel, and then turns it up on its end and then down the conveyor. I don't know if any of you have been to some other hot mills. We do not band in the belly down position. We band them when they're standing up down the station. Some hot mills have automatic banders with their coilers. We have a little bit different setup. There's no here. If we miss, cobble sounds like a train coming through the building, but we don't have those very often. I've never seen one, and I've worked here for 2 years, so. Before I go on to the metallurgy, does anyone have any questions about the hot mill itself?
What's the least amount of thickness that the hot mill?
We can roll 063 gauge, maximum of 1/2 inch. We can coil 1/2 inch.
Are your rolls in the 4-roll stands, are they directly over each other? The
Yes.
working rolls, I've seen where there's technology where they try to maintain the center gauge as close to the edge gauges by crossing rolls.
No, ours are not crossed. Ours are directly over each other. That's an interesting concept.
The gauge gets real too on the heavier. 170 like a mill tolerance would be like, let's say, 16. What we see a lot of is the head and tail, still the gauge is really there. It could be like 180 on 170, 110. The gauge would be way out. Yeah, I can go through. It would be pretty consistent throughout the middle. Just wonder now.
Part of that is probably due to the lack of tension on the IDs and ODs. When the strip is in the 7 finishing stands, well, there's tension on the strip between the stands, but then as the strip comes out of F7, it's just going down the runout table until it gets to the coiler. No, that might not. That wouldn't affect gauge. I'll have to ask about that.
Just we see, especially like gauge variance, OD would be heavier than one of these runners. Routing time on
Yeah, we typically run to ASTM standard tolerances. If you want smaller than that, you'll have to make.
Maybe just even almost 6 feet or something.
I'll let the operating folks know. Are there any questions about the hot mill? Yeah.
Exactly the scale again?
Scale is, well, it's iron oxide of a version of rust. Mm-hmm. No, I won't talk about that. I was just thinking about a lot of things run through my mind when people ask questions. I was just reminded of the fact that steel that's above 1600 degrees, is not magnetic. And just remembered that. Most people don't know that. Gamma iron, steel in its austenite phase above 1600 degrees is not magnetic. You have to wait for it to cool down to about 1400 before you can touch it with a crane. I don't know where that came from, but now you all know. Anything else? This will all start to make sense when we get out there. I realize it's very difficult for you to imagine, looking at a flat piece of paper what this looks like. I'm trying to get them to let me make this into a slide presentation the way Keith has it for the BOFs, because that's kind of neat. But, it's impressive when you see it. It's brute force at its best. Okay. Now this is dry, but we got to talk about it. My boss says, here's the presentation. Okay, I'll work with it. The title, Important Characteristics of Steel Controlled in the Hot Strip Mill. And this is just kind of a summary of what I've said before. The furnaces are 2,300 degrees. There's that number again. The temperature coming out of the last roughing stand, R5, is about 2,000. We finish between 1550 and 1650 degrees. And coil, usually around 1,000 to 1,400. Coils are really spongy when they're this hot. We'll do it. The width we measure coming out of F7. That's the final width that we will report, unless it's being trimmed, and then we'll report the trim size. We're capable of rolling between 24 and 76 inches wide on an 80-inch mill. And we can alter the incoming slab width plus or minus an inch. The gauge is measured when we come out of F7. We can roll 060 to half an inch. Slab thickness out of the caster, out of our caster, is 10 inches. And again, the thickness coming out of that last roughing stand is an inch and a quarter. We measure profile, which is the difference in the thickness between the center and the edge. There aren't industry standards. There are just what customers prefer and what customers want, which differs from customer to customer. And the reason why profile is important is because it can result in shape problems if it isn't controlled. If you have a wedge or if you have a ridge, that can cause problems down the line. Yes?
You're coming out of the finishing station between 1550 and 1650. Then you go into coiling, and then obviously the coil will either go to the customer or sit and cool someplace. How much of a variation in your width would you see from finishing to complete cool down?
For shrinkage? I do not know.
That'd be considered a millage, or is that?
That would be millage.
Yeah.
What's this running? You say it runs about 30 miles per hour.
That's fast.
Okay. At what gauge are we talking about? Like when this stuff's actually what we call recoiling, or we call on the coiler, about how fast is that going?
The coiler? It's got to keep up. 30 miles an hour.
I just,
I have written here
what
feet per minute.
I mean, at 060, is it going that fast, but at half an inch, is it still able to maintain that speed?
No. No, it's much slower.
How slow is that?
Oh, I don't know. I do not know how fast, how slow we can go. How slow can you go? I do not know. Because I've only worked here for 2 years. Give me another year. Maybe I could get that question. No, I don't know how slow it is. Yeah?
Is your coils stored on the edge or on the flat surface?
Both.
Both. At 1,000 to 1,400 degrees, will that create a flatness in the steel, storing it on
If it's belly down, it can. Some chemistries are more prone to that than others. I work with one chemistry that you get even near 1,200 degrees and it just sags right down. I'm trying to think of a way I could put something in the eye to hold it up. I'm still working on that. And I think about it at night. How could I get those to stop from collapsing? Yeah, and others they're just happy as punch, sitting belly down. If we're going to be processing it inside somewhere, we leave them eye up. But if it's going to be sold as a black band, they're put belly down within a day or so. You've heard about flat coils before. there any other questions? Okay, just some quick things. And this is, I'm sure this is out of order from your book. 1994 was a real good year for us, so we like to show you just how fast we can go. In 1994, we produced almost 4.5 million tons out of the hot mill. That was an average of 374,000 tons a month. There's our tons per hour, 618. So we can empty out a furnace in an hour. That's pretty good. Our yield that year was 98%. There's our BTUs per ton. And well, you can figure out how many slabs that is. We're hoping to beat that this year. We have big plans. Okay, I know you've all been waiting for this. Let's get into the fun stuff. The metallurgists just love this part. Okay, back to college. The usual goal in hot rolled sheet steels is to produce a ferrite perlite microstructure. And the mechanical properties of hot rolled sheet are controlled by the amount and the type of the elements dissolved in the ferrite, which, if you're using solid solution strengthened steels, HSLA grades, manganese and silicon, those type of elements. It's also controlled by the volume fraction of the second phase, where ferrite's the first phase, and the second phase is either perlite or bainite. Properties are controlled by the ferrite grain size, and then the number and the size of precipitates. If you're using precipitation strengthened steels, that's vanadium, columbium, those type of strengthening agents. If anyone comes up to you on the street and says, "How hot is a reheat furnace?" you'll be able to say 2,300 degrees. This is just kind of a visualization of what we're talking about temperature-wise. Again, here's our furnaces in the soaking area. The roughing stands only take it down to about 2,000 degrees. The finishing is where a lot of the temperature comes out, down to about 1,600. A run-out table with all the water, all those banks of sprays for our cooling. And then coil cooling is kind of, comes this way. Oh yeah. And if you notice the time scale here, this is 4 minutes. So it's fast. My favorite, the iron carbon equilibrium diagram. I don't know which one of these you have in your book, if it's this one or this one. We'll look at this one first because it's easier to look at. Out of order, again, I know. But this is where all those important temperatures come into play. I mentioned austenite, the steel that's above 1,600 degrees is not magnetic. That's this here, austenite, known as gamma iron. And this is Fahrenheit. This blurry word here is temperature in Fahrenheit, and there's 1,600 degrees. So on this diagram, when we come out of the finishing stands, we're right in here somewhere. And as the steel cools, all of our steels that we run in the hot mill are within this box here, in this column. The carbon percentage is along the bottom. This first line here is 0.5% carbon. We don't run anything that high. As the steel cools, you'll see this little area here is called ferrite and oxide. There's where the first phase forms, ferrite. And then we go through this is the beginning of the transformation, and when we get done, we have perlite, Fe3C. For the metallurgists that is familiar too, you know what I'm talking about. Others, it's quite a stretch. I understand. I have some. No. No, this is all plain. Well, plain carbon for the most part. Plain carbon and some alloys. No, we don't run any stainless.
You mentioned that it was non-magnetic at 1,600 degrees. What's the significance of that?
Well, in the hot mill, it's kind of a big deal. If we have a problem, we can't move it. And we sit and wait for it to cool down. Because no one's going to get out there and push it, out of the way. Or could we have to wait for things to cool down for our cranes to come over with their magnets and move things out of the way? Yeah, it's important that we keep things moving. So otherwise we have to wait a long time. Just some notes here. When hot working material, the high temperatures above 1600 degrees allow the grain structure to kind of, I've mentioned this before, redeem itself. When you're working the steel and pushing it and shoving it around, the microstructure kind of gets twisted around. And if you keep it above 1600, it lets it relax and get back to its natural state. Versus coil rolling, like temper passing a coil, you're really doing, you're making the structure more brittle. That's right, you can skin pass things too hard. I'm sure as we all have found out. The finishing temperature sets the direction of the grains in the microstructure, and then the coiling temperature at the coilers determines the size of the grains. And the grain size determines the physical properties and the formability. The grain size, which is set by the temperature, is also set by the chemistry. And this picture kind of, it should be obvious which one of these is weaker or which one is actually stronger. A low carbon, a plain carbon steel like 1008 or 1006 material has this much larger grain structure versus a microalloyed steel, which is a lot stronger with the much tighter grain structure. So if you think, I'm a crack trying to get from this side of this piece of steel to the other one, well, it's a lot easier for me to get through there versus a crack trying to get through here. So this is what we're setting with our finishing and coiling temperatures versus depending on what kind of chemistry it is. That's typical microstructures, what you'd see of like 1008 versus, I don't know, it's an HSLA crate, I guess. Here's how we're doing it. Carbon steels, yield strength and KSI along this side. For those of you who like megapascals, you can look at this column. Carbon steels are down here. Grain size, like I said, which is set by the coiling temperature, coiling temperature is listed across the top. Carbon steel here with the much bigger grains, and they're for a lower yield strength. HSLA grades, the solid solution strengthened steels, are a jump up in strength, and then the precipitation hardened steels I've seen it get up here. Just for your information, we do things like everyone else. We measure yield strength, tensile strength, and total elongation. That's what we report on your test reports, if you ask for test reports. We've recently made a major upgrade to our hot mill laboratory, our testing lab. We purchased a new milling machine to mill out our tensile samples and a new tensile machine. Our Tinius Olson machine was older than the one we had in college. You can imagine how old that was. I think that was the first one they bought here back in 1965. So we have a lot of brand new equipment. It's all computerized, and we're looking forward to using it. It's not plugged in yet. It just got here last week, so we're itching to get it running, which should, that's really going to help out with our customer service. We'll be able to get more samples through faster, because I'm sure at one time or another you've heard it's in the lab and we're testing it, so we'll get the tests out faster now. And the guys that run our lab really like the new equipment, so it's a bonus too. They aren't afraid of using a computer. So a summary of this really dry metallurgy: we have to reheat at a sufficiently high temperature to dissolve the microalloying elements, be it columbium, vanadium, or titanium, or alloy of your choice, and that's 2300 degrees. We refine the austenite grain size, that non-magnetic stuff, by recrystallizing during the high temperature roughing passes. Recrystallization, that's the redeeming of the grain structure, letting it relax again after it's been worked. For the finest ferrite grain size, you want the smallest grain size you can get, the biggest bang for your buck. The later finishing passes should be below the recrystallization temperature to develop a pancake austenite structure. The grains are a different shape. I can explain that later. We want to make sure we always keep the finishing temperature, which is the temperature coming out of the last finishing stand, the F7, above that austenite to ferrite transformation temperature to avoid rolling them together. We roll austenitic steel. We've started rolling ferritic steel, which the Europeans do a lot of. We deliberately roll it below its transformation temperature, which is, so you end up with a ferrite structure instead of ferrite and perlite. You end up with one phase. And that is supposed to provide much more formability, drawability. We're in the experimental stages that we've rolled 4 coils so far. We control the austenite to ferrite transformation temperature. Again, for the finest size, you want the biggest bang for your buck. For the higher strength levels, we'll precipitation harden the ferrite using vanadium and or nitrogen additions. And for microalloyed steels, we want to make sure we use a coiling temperature below 1150 to avoid a low strength in the body of the coil. And that's from, if you coil it higher than that, it gives these microalloys, the precipitates, a chance to grow because it's warmer and it sits there and bakes longer. And if they grow and they get big, then you end up with like nodular iron. It makes it brittle versus strong. So that's why we do the things we do. And it's all controlled by a computer, a really big computer. Types of hot roll steel that we have here at the mill, commercial quality, which is ordered by chemistry. I was mentioning 10.6, 10.10, 10.12. Any mechanical testing we do is for information only. This is not supposed to be used for difficult forming applications, although some customers use it successfully. And it's used for all types of surface requirements, exposed panel stock, unexposed tubing, brackets. Drawing quality and drawing quality special killed DQ, DQSK is a low carbon product. We'll aim at mechanical properties. There's a couple of ASTM specs that we will work to. We'll often guarantee this kind of steel to make a part. Typical applications: lawnmower decks, automotive parts, oil filters. Structural quality. We'll have required mechanical properties, minimum yields, and tensile strengths. We will meet those. These kind of steels can be strengthened with carbon, manganese, silicon, solution strengthening, and sometimes we will use microalloyed steels. Typical strength levels is 30 to 55 KSI yield. And there's some applications listed: A36 strip plate, metal building components, and tubing again. HSLA, high strength alloy steel, also has required mechanical properties. This application we will use microalloyed steel, and this is just improved formability over the structural quality. And the applications: automotive parts, wheels, and line pipe. So you know that we are always striving to improve. We've been working on a modernization in the hot mill, and it's ongoing. We installed Part A here in the finishing mill, the finishing stands 5 through 7. We put in hydraulic loopers last year ahead of schedule. We put the first one in, and it went in so easy. We put the other 2 in during the next outage. HAGC, hydraulic automatic gauge control, computer systems will be added this year. Those are going in right now. And we're also adding positive roll bending to those 3 stands with shape gauge, which should also be finished this year. And the benefits listed to improve our gauge performance from 95% at plus or minus 2 mils to 99% plus or minus 2 mils, which will give us the ability to roll to a 3rd standard tolerance. And we're hoping to improve our shape to plus or minus 35 I units. Note C, the improvements will make us competitive with any domestic or foreign hot mill in shape and gauge. We'll improve our yield through less reclamation, less pinching, and less cobbles. And will also allow us to roll lighter gauges without requiring skin passing. Currently, if you enter an order for under 100 gauge, or maybe it's 090, we request that it be skin passed to ensure flatness. You don't have to if you don't want to, but we recommend it. When we get these new, we get this modernization finished, we should be able to go lower without the skin passing recommendation. And for those customers that buy cut-to-length product from us, this is one of the first slides to get retyped. We've done some modernization to our cut-to-length line. They put in cone gearing and do screw-down drive motors, which will greatly improve our roll force and therefore our flatness. They put in a new X-ray gauge, a DMC 480. It's been working very well, which will give us edge-to-edge scanning ability and just a lot more accurate data on gauge overall. We also installed a Bradbury hydraulic leveler, which has been working out well, which also improves our flatness and just overall quality.
Yeah, what thicknesses are you running on there?
We can go to 1/4 inch. We've also made some changes in the way we use our looping pit. We basically don't use it anymore. We've been running our strip very shallow in our looping pit, and that's also helped with our shape. Not getting the, you could say, coil set back in after it comes out of the leveler. So, and there's a project completion date of 2nd quarter '96, and it was done last year. So. That's the end of my slides. So who has any questions? See it? That's the best way to learn what's going on, is just to be out there and see it. So.
If a product goes to the combo line, does it ever go to the finishing mill after it gets cut to length, or it's basically complete at that point?
Cut to length is the end. Yep, once it's sheets, that's it. But if you order pickled cut to length product, we'll send it to our cold mill to get pickled and then brought, or some cases it gets pickled outside and brought back in. But yeah, cut to length is the last step for that line.